the one and only. The problem this time around is not the laptop, which is a positive. Mm. Yes, that's very good. Oh, that's very good. Very good. Oh, yes, that is actually very good. Perfect. I think we are. Are we all set? I think we are. No, I think we're all set. Oh, maybe I do. Should I be wearing this? Yes, little, I think it's there.
Just clip it to your belt or something because I think the antenna is bit. Yeah. That's at the top. Not working? I tried it yesterday. Yeah, that's it. Oh, it's not even. No, that will be good. I'll try it. Look at the big shot. We have a decision. So we can change the battery. Or Mate, maybe you can start off with mic and we'll try to. Oh, cool. Oh, is it? Yeah, that's very good. Maybe okay, that's good.
You did the right thing. You see, this is.
As long as Mate was.
No, I'm fine.
Okay, I'll say. Okay, let me. Used to talking anyway. Hello.
Maybe to the bottom.
That's another.
Okay. Here, this one will work. Here, this will work. This will work.
Hello.
Yeah, that does it. Definitely does work.
Already works.
Yes, that is.
Hello. Yeah. Okay. Let me welcome you back to the Sat+Smt workshop, the final day, the finale. And what better way to start it off with Mate? So Mate obtained his PhD from INRIA in 2009 and has been working both in academia and industry on formal methods, breaking lightweight cryptographic primitives, and IT security. So we are all aware of his work on CryptoMinisat, and he has worked with Kuldeep and even me on multiple projects like ApproxMC, Ganak, and as well as CMS Gen.
Yes.
My phone, okay. He has also helped reverse engineer. My phone is not Okay. So it also helped reverse engineer. Yeah, I don't know why it does all the time. So it's reverse engineering, looks like my phone. I think it can help. And break the lightweight ciphers, high-tech 2, MegaMOS, among others, and has been a using combination of SAT solving, algebraic cryptanalysis, GPGPU, and FPGA programming. Very interesting. I did not know about this. Okay, I'll talk to you. He's currently employed by the Ethereum Foundation to work on formal methods building for Ethereum ecosystem and regularly does research at NUS. It's a great privilege to have Mate here with us, talking about SAT pre-processing. The stage is yours, Mate.
Thank you so much. Thanks for the kind introduction. Yes, thanks for having me. It's actually been really wonderful to be here. I'm going to be talking a little bit about SAT pre-processing. It turns out that a lot of what modern SAT solvers are doing has little to do with CDCL and a lot to do with SAT pre-processing. If you have a look at the latest and greatest SAT solver that won this year, the SAT competition, it's basically Cadical-SBVA. And if you check SBVA, it's a pre-processing. And this has been the case for a while now. There are, of course, cases where we improve the heuristics. You could call it strategy. Maybe you could call it tactic, would be maybe a better. I'm not sure it really qualifies as a strategy. And sometimes we change some things about CDCL. In particular, I'm sure a lot of you have heard about first UIP. Most or many SAT solvers nowadays do all UIP, which was a way of doing it before as well, but it was not really paying off. And now it is paying off. So we have switched from first UIP to all UIP. And in terms of CDCL, that was basically the biggest change in the past, maybe quite a while. Sometimes we add some extra heuristics into CDCL, and there's of course this VMTF versus VSID's way of running. So now we run 2 heuristics instead of 1. But in general, the resolution part has stayed more or less the same. And so instead of fixing or changing that, we've been improving on pre-processing. And pre-processing is effectively a rewrite system for CDCL. Well, for a system to help CDCL, because it's really a rewrite system for the CNF. And basically, CDCL is pretty poor. For example, if I give you 2 clauses, A or B, and the other one is A or B or C, CDCL will never remove A or B or C, even though, of course, it is implied by A or B, because A or B is a stronger constraint. So CDCL will never do that for you. It also will never remove variables, right? So if I can somehow remove a variable and put its sort of description or what we would call resolvent back into the problem, solve the problem, then somehow extend the solution back to a full solution, that would make it a lot easier to do things. And actually, this work was done by Armin Biere and Nicolas Sörenson back in basically for Minisat, just before Minisat came out. And that's why Minisat was so incredibly powerful, because it had this one pre-processing. Everybody remembers Minisat, of course, engineering-wise, it was insane as well. It had a lot of good tricks, but without BVE, it wouldn't have gone anywhere. And so BVE is the bounded variable elimination, which is this removing of variables. And sometimes CDCL can simulate some of the simplifications that I will talk about here, but basically by accident. Like if it does it, it really is by accident. So the idea is to take this CNF, make it into an equisatisfiable CNF, like a CNF that is satisfiable if and only if the previous one is satisfiable. In fact, we can even make sure that we have the exact same number of solutions that we have previously, and we can make sure that we can, any solution we have for the original CNF, we can extend the full solution to the final CNF. So we're gonna effectively have a smaller CNF to solve. So I just want to give you a little bit of a teaser of what this thing can do, because I think it might be sort of underappreciated. So this is one CNF. We start with 7,600 variables, right? I think maybe you can see it. Maybe I can make it a little bigger. So it starts with 7,600 variables, right? It starts with 40,000 clauses, a total of 158,000 literals in this CNF. So you see at the bottom, this is the problem we're trying to solve. And at the top, I've already simplified it. Actually, I can also show you how many seconds. It was 12 seconds to run that simplification. And it ends up with 387 variables instead of 7,000, right? So that's slightly smaller, we were going to call it. And 3,000 closes and 16,000 literals. And this is actually quite funny because this is not only equisatisfiable, this is actually the same exact number of solutions as well, because this is for counting. We wrote this tool for counting. You can actually download this tool and use it right now. So this is what we're going to be talking about. And there's no, I mean, I haven't done anything that there's no CDCL in here. There's no CDCL. Of course, there's resolution in here, and I use a bunch of other rules as well. But this is just pre-processing. So this is where we're at. And this doesn't even include SBBA, by the way, in case you want to. So it doesn't even include the newest and the hottest and the coolest thing out there. Maybe I'll put it in when I have a little bit of time. Okay, so this is what we're going to be talking about. And hopefully by the end of this talk, you'll understand why we get from that place to the other place so quickly and so. Yes, sure, yes. Oh, the input variable you should ignore. It's something that I was hacking around a little bit. So forget about the input variables. It's the question here. Well, basically we started with 386 variables, and then eventually that was divided into input and output in the sense that the input was what you normally count over. So we're going to count over the 142 variables, and then 245 is the one that we're not counting over. The one at the bottom didn't have any of that. It was the original formula didn't have any input and output variables, but what we did is that we computed input and output variables with our tool called Argent, because basically what we said is that you could count over 7,628 variables if you really wanted to, but what's the point? You can just count over the 142 and you'll get the same result. So the same exact count. Basically for this, you have to compute that all those other variables are fully defined by these 142 variables. Like their value is fully defined by the 142. Once you compute that, then you can remove all the other variables except for this 142. Yeah. In the final form, we also unfortunately have 245 variables that we know are not, and we don't need to count over, but we can't remove them, because if you remove them, then the formula explodes in size. I mean, eventually you can't, if you try to express AES in CNF, for example, in 128-bit key, so all you really need is 128 variables, that's going to explode. It's going to be an exponentially large description. So we need these extra variables, these intermediate variables, sometimes they call them, to sort of make the formula more sane, not so large. But did that explain? Okay, that's good. Yeah, so this is the tool that we're writing. Okay, so real-time system CDCL. Let's start with the simplest one. I'm sure all of you would come up with this within less than 5 minutes. So you take all literals, you create a new decision level in the Sat solver, you enqueue this literal, and then you propagate this literal, and then see what happens. Is it going to be Sat or unsat? Well, if it's we backcheck, of course, we undo the new decision level and the propagation and everything. Oh, is it like? Okay, let me try to. And then we see if we failed. Well, if it failed, this, if I enqueued A and propagated and it failed, like something went wrong. Ooh, that's kind of, yeah, okay. It failed, then that's a bit of an issue because it means that the not A must be true. Right? Oh, maybe now. Oh, that's better. Thank you. So then not A must be true. So we can try this for every single literal, of course, and now we're going to set some literals. The nice thing here is that we're not calling a full Sat solver, none of that thing. All we're going to do is propagate. I mean, it's quite easy to do this. For example, there's a not A or B, not A or not B. You set A to true, and you said A, let's say not A or B, not A or not B. You set A to true, like B gets set to true because of the first clause, and not A or not B means, when A is true, B must be true as well. Well, B must be true and false at the same time, so that's unsatisfiable. Then we just learned that A cannot possibly be true; it must be false. So you can discover this with propagation very easily. Oh, sorry. So this is just pure propagation, very simple. You try every single literal. Okay. Stalmark's method is a bit more involved, but it's not very difficult. I'm sure you can figure this out also quite quickly. Although it is patented, so beware. If you do figure it out, you have to pay a patent fee anyway. I think it might have expired. Like Armin was working around this thing all the time. I never paid the patent, I have to admit. So well, what you do is that you take the same thing as before. So it might fail again, just like before, but let's assume it doesn't fail. And now you enqueue A, you get a set of literals that get propagated, right? So let's say you enqueue A, you propagate it, and you got B and C and D. And then you say, okay, well, let's forget about this for a moment. I'm going to enqueue not A. So I enqueue not A and propagate. Well, let's say that you propagated B and C and G. Well, it happens that the B and C were in both sets. And I mean, A needs to be set to either true or false. There's no, like, it's not like there's a third option for A, right? So A must be either true or false. So if you tried propagating A and you got some set, and you tried propagating not A, you got some set, well, the intersection of the two sets must be set. Like they must be set to that value. Because if you have a final solution, you have some kind of solution at the end of the solving, well, A must be in that solution. And if A is in the solution, then one of those things must have propagated. So the intersection you can always just set. And this is basically a Stalmark's method in a simplified way. This is actually a complete method. Stalmark does it for all. So this is obviously true only for one variable. You can do it for two variables, and then you have to, instead of doing 2, you have to do 4. If you have 3 variables, instead of doing 4, you have to do 8, etc. Because you have to try all combinations. But that's basically Stalmark's method. It's quite simple and works quite well. So quite effective. Yeah. Oh, that's kind of annoying, the little switch camera thing, but it's backbone. That thing is supposed to say backbone. So backbone is basically, we're going to use an actual Sat solver to do the same thing that I just described. So you say A, let's set A, let's see if A is true. So is there a solution with A is equal to true? If there is no such solution, then A must be false. So this is kind of nonsense in some, right? Because this actually uses the Sat solver to figure out what like to help a Sat solver that doesn't. But the thing is that this is really useful for model counting and other kind of things that are much more expensive than just finding a single solution. So what you're basically saying, conjuncting F with literal, solve it. If it's unsatisfiable, we know that not of literal is implied by the formula. So I can just set it, right? So this is called backbone, and you can do way better than this. There's an actual paper this year by Armin, if I remember correctly, on backbone called mini bones. There was a mini bones, and then he did Cuddy-Beck. It's Cuddy-Beck. Mini bones was the original. Cuddy-Beck is the new one, and it's very cool. It doesn't just do it one by one. That's of course the stupid way of doing it. The correct way of doing it is doing it like bunch by bunch, because you're expecting there to be more than one. And you can also do some cool things, like, for example, you solve the problem and you get a solution with A is equal to true. Now, I mean, clearly A is not forced to false, because there's at least one solution where A is true. So you can sort of cache all the solutions you have ever seen and figure out that some of the things cannot possibly be set to some values, so you don't even query it. And so you can have some, yes?
That's like when say, all right, let's say half of it. That's viable. I know.
Yes, correct. So you can do this. Yeah, exactly. Yeah, you can do that. And if you combine that with this cache method, then you can even throw out some other bits and pieces and like be even smarter. And Cuddy-Beck basically does all these tricks in one big. You can even do the reverse. So you can when you get an unsat, you can even examine the proof and help next time. So yeah, there are some nice tricks. Okay, so this is actually running a full Sat solver to have a Sat solver, but you don't normally do this, of course, if you're just wanting to know if there's a satisfying assignment, because this will always give you a satisfying assignment as part of its own job. But if you do something like model counting, then you do this, and the tool that I showed actually does do model counting, so that will run this to completion. Okay, equivalent literal substitution, again, very trivial, not a big deal. So here you have A to B, B to C, C to A. So there we have a loop here. So if I set A to false, then B gets set to false, C that get to false, and which wants to propagate A is false. And the same thing for the other way around.
So you see that at the bottom right, you can substitute A is equal to true. That will set C to true. And then, then the second clause, you substitute C is equal to true. It forces B to true. And then the first clause, if you substitute B is true, then forces A to true. So this is a full loop. And all you do is do strongly connected component analysis, which was talked about yesterday with Tarian's algorithm. And we're done. All the loops, the strongly connected components are all equivalent. So A is equal to B and C. Well, you remove B and C and you keep A. That's it. End of story. So this actually is not. You can. Well, yeah. So this is quite nice, and it removes a bunch of variables. And this can actually be. Oh, I touched it again. I'm not going to touch anymore. Yeah. So this is also very quick. It operates only on the binary closes. Quite a lot of fun. Okay, so talking about binary closes, no, subsumption. Let's go to subsumption. Okay, this is very trivial. I mean, there's nothing much here. As you can see, the three clauses and the second and the third clause are clearly implied by the first clause, so there's no point in having it. So we're just gonna remove it. There's no point in having it. The real trick here is actually not the replace part there, because I'm sure all of you would have come up with this. The really hard part is how to do it efficiently. Like notice that this, I think it is me, but who knows? Notice that this can be done actually to Confluence, which is quite nice. SCC can also be done to Confluence, so equivalent literal replacement can also be done to Confluence. So Confluence meaning that no matter which order you do it, eventually you end up at the same place, which is quite nice. This one as well, so you can just do it in whichever order you want, and eventually you end up at the same place. The question is how to really do it, like efficiently. And the way they do it, also at Minisat. Well, I think it was also already in the same. Well, basically, Minisat took a bunch of things from. That's very strange. Sorry. Satellite. No, it was Satellite. It was Satellite. So Satellite had this already, which was already also written by Niklas In and Niklas Zörensson. And the way they do it is that they do it in reverse fashion. So instead of saying, is A or B or C, subsumed by something, you do the reverse. Is A or B subsuming something? Which is much easier to do if you do it. If you start writing the code, you realize that it's a lot easier to write. And then they also use a Bloom filter, because what you can do is that you can make a Bloom sort of a hash out of A or B or C, A or B, everything. So each and every clause, and then do a very quick check whether this will ever subsume it or not. And if you do the quick check and it succeeds, then you do the full check. Is it really subsuming it? And this will make it significantly faster to run. Oh, that is supposed to be. Yes, I'm wrong. Yes, there's like, yes, absolutely, I'm wrong here. Yes, sorry about that. We're gonna very quickly fix it, or maybe not. But yes, so that is supposed to be here. It's supposed to be a not A. I'm sorry. These are all not A's. I don't know what's happened here. Sorry about that. They're all not A's, and this is, yeah, that is at least correct. But yeah, these need to be not A. No, these are not A's. What is B and B? Okay, there's a sorry about that. I don't know what happened there. Yeah, so just forget about what's on the right. You remove this bottom two clauses. That's the end of and that's the whole thing. Yes, sorry about that. Okay, so strengthening, weakening. This is actually very annoying because you need to do both, and they are the reverse of each other. So let's start with strengthening, which is quite easy. So what you do is that you take these two clauses on the left, and if you do, so what you can do is you resolve the two clauses. So let's resolve the two clauses on the left. And if you look at this notice thing here, you will get A or C or D, right? If you resolve them over B, you see that you get this clause out of it. Well, this clause happens to be small, like a subsuming this clause. So you can just remove it, this B here, and this is called self-subsuming resolution, because you do resolution and it happens to subsume one of the clauses that you were resolving over. So now you can strengthen this clause. It's called strengthening because you remove the literal from the clause, and obviously this strengthens the constraint, because the constraint now can be satisfied with less number of different potential solutions. So the logic here, of course, is that A or not B can subsume can be that anything that A or not B can subsume can be strengthening to remove not B, and everything that not A or B can subsume can be strengthening to remove not not A. So you just do a subsumption check, actually. Just you run the same algorithm you ran before, but now you're going to, instead of removing the clause, you're going to remove a literal. I don't know if this makes some sense. It's kind of strange because the original clause is A or B, but now you're going to do the subsumption check on A or not B. And if this subsumption check succeeds, sorry about that. If the subsumption check succeeds, then you're gonna remove the not B. So this is a bit of a this is all rewrites. So this we're gonna rewrite our set of clauses into something nicer. And so the implementation is again reverse. And actually what we do is a slightly more tricky version of the subsumption because we're going to subsume over variables rather than literals and then do the right thing. So then you can just check once like A or B as variables, not as literals. And then, of course, you're going to end up with both of these and then you're going to remove the correct literal and you'll be happy. So this the implementation is a bit more tricky, but not a big deal. You could just use subsumption. If you have already implemented subsumption, you can just use that. The more tricky version uses this with variables, and then your Bloom filter needs to work over variables and not literals. So it's going to be a slightly less effective, but still okay. Okay, so that's strengthening. The weakening is literally the same, except in reverse. So you're going to add the not B, which sounds really stupid, right? Because why would you add the not B? But because now you just made your CNF weaker. Like it's actually harder to solve. But the reason you do that is somewhat much later at the end of this presentation. You will see that this is actually quite useful. Sometimes you want to weaken temporarily and then hope for the best. I'll explain later. It's quite nice. Okay, binary implication graphs. How are we doing with time? Okay, so transitive reduction. This is actually very simple. So if I set A to false, right, then B gets propagated to false as well. And the second, that's the first clause. Then if I set B to false in the second clause, then C gets propagated to true. So what's the point of me having A or C? Because A or C does the same thing, right? So you set A to false, then C gets propagated to true. So this is redundant. The last clause is actually redundant here. And you can show that, of course, by just doing resolution. So this is the resolution. This is the resolvent. So clearly, you can just remove it. But the thing that's interesting here is that this is over a binary implication graph. So there's this, you can draw a little graph like A goes to B and B goes to C. And if you think about it, what's the first two clauses are doing that exactly. So A goes to B, B goes to C. And now there's an extra arrow from A to C. Well, what's the point of that extra arrow? We already know that implication, right? We can just walk this graph. So what you do is transitive reduction and you remove that extra clause. There's no point. Okay. Because this will always be implied. No matter what you do, actually, you said A or B or C or whatever, all the things will be correctly propagated all the way through everywhere. So that's going to be fine. Like you're not weakening propagation in any kind of way. Okay, and hyperbinary resolution is kind of a nice addition, fixing, whatever you want to call it. So here what's happening is that there's a line from A to B and there's a line from A to C, right? And then there's sort of a little bottleneck there with B or C or D. So you go from A to B, you go from A to C, and then from B and C you can go to this clause, and it will propagate D. So if I substitute A is equal to false, then suddenly D gets set. So there must be a clause that says A or D, because that is clearly implied here. I can just do the resolution. And this is called hyperbinary resolution because you can do this really quickly, and you can get up with these kind of clauses. And of course, the question is, what's the point of me adding this clause, right? This was already implied by the previous thing on the left, so why would I do that? Well, the reason why I do that is that imagine if I do D is equal to false on the left side. Well, nothing happens. So I put D is equal to false, I call propagate, nothing happens. If I do D equals to false on the right-hand side and I say propagate, well, A gets set to true. Right? So the one on the right is actually helping me in case I'm trying to propagate things quite a lot. And not only that, if you think about it, that clause on the right-hand side is a binary clause. So when I'm looking for equivalent literal replacement, I can use it to find new equivalent literals. So this can actually help me find things like, let's say, A is equal to D or F or whatever. So this can help me in other ways. These things always interact. There's one of the biggest pain in doing all these rewrite rules that eventually you realize that all these things all the time interact with each other and can be quite painful. But in this case, it's quite useful. It interacts in a good way. I actually said redundant binary close because, of course, this is not needed. It's already implied by the formula. So you can add it, and it can be there. And then you just say, OK, well, that was a nice day, and remove it later on if you want to. For example, if all you really want to do is compress the formula, you can add this temporarily, see if you can do strongly connected component discovery with it. And if it didn't help you so much, then you're just like, well, it was a good one, and I completely forget about it. It's implied, so there's no need. Good. OK, this is actually really fun. Same thing, but now we're going to have a little more fun. This is Marijn, Matti Järvisalo, and Armin Bier in 2011. I really like this. I had a very poor man's version of this system, like a really poor version of this system. And they came up with this, and I was like, I love this. So this is the same idea, right? So these are binary closes. H goes to F goes to C, D goes to A. There's the closes up there, so you can just read them as well. But the question is, does H imply A? Like that's what you want to discover, let's say. Well, if you want to discover that, one way to do it is you enqueue propagate, and spend all that time propagating and everything, and eventually end up in A, and you're like, yes, it does imply it, I know it. But what's the point of doing that if you can do the following? You propagate H once, only once. You do this thing, the thing that you're going to do is you're going to start at, let's say, number 17. That's your start. And you're going to walk this thing in a depth first search, OK? So 17, then we go to 18, then there's nowhere to go here. So we're going to do another thing called these are timestamps. There are 2 timestamps. The first one is your start point, and the second one is going to be your end point. So this is 17. You go here. This is 18. I have to close this. This is the end. I have nowhere to go. So this is 19. I go back here. OK, do I have somewhere to go? Yes, I go here. 20. OK, do I have somewhere to go? Yes, 21, 22. Oh, I have to close. There's nowhere to go. 23. Go back up, there's nowhere to go. 24, go back up here. Is there anywhere to go? Yes, here. 25. Okay, I have to close this, so that's 26. I go back here. 27. Ooh, 28, we're done. Happy. Okay, so how do you figure out if A is implied by H? Well, the H happens to have the starting larger than the H and a smaller closing than the H. And this is it. You just do 2 checks on the starting, 1 check on the start and 1 check on the end. And all you need to do, actually, if you're trying to look at a close and you see that, hey, is something in it already implied by the other one? Remember, if it's implied, I can remove I can remove the literal. Remember this literal that we can remove? If if A implies B, or A implies not B in this case, I can remove that literal. So how can I do this? Well, I sort this close here. And then I can just do the check on the, OK. I can just do the check on the, I can just do a check on the stamp thing. I think it's actually here, not there, but maybe I'm wrong. Anyway, so this kind of thing allows you to do you walk this binary implication graph once by propagating all the different literals that you can think of. And then you can use these timestamps to strengthen all the closes, including by binary closes that are not even in the formula. Because what's happening here is that this is effectively telling you that there is a binary close between H and A, but it's kind of implied by the formula. And figuring that out would be quite painful. So instead of doing that, you can just do sorting of the closes, and you can be done with that. So it's quite fun, and you can do subsumption and self-subsuming resolution with this thing. And of course, it's more powerful than just using it. I mean, of course, I can just use these closes here, right? And of course, you will do that. But this one implies more than that, because this will also say that there is actually a binary close between H and A, and you can use that to do subsumption, which, I mean, of course, when you look at this, that's not obvious at all. Yes?
Arrow is set H false.
Yes, exactly. If you set H to false, then F is implied. And if you set D to false, then A is implied. The numbers are basically your starting and ending state. So you start here at 17, and you walk this graph in a depth first search. So this is 17, this is 18. You go here, you have to go back. I mean, depth first search, the way it works is that there's nowhere to go, so I have to go back. If I have to go back, then I add another number, so the next number. So that's going to be 19. And I go back up here. And then I was like, is there somewhere to go? Well, depth first search, so I do. And then I go down here, and it's going to be 20, and then 21, 22. I have to close 23. I have to close 24. Go back up. Is there anywhere to go? Yes. 25. Then I close 26. I go back up 27. I go back up 28. I'm finished. So I just like sort of did a magic numbering of these literals. And now next time when I'm looking at these literals, I can use these magic numbers to figure out if there is a clause called not H or A, right? Because this, yeah. Oh, sorry, that H or not A. Sorry, H or not A. Yeah, sorry, yeah, H or not A. Yeah, correct. Oh, that is wrong here. Oh God, that's like it's the second bug you're finding, but yes, H or not A. Yeah, correct. Yes. So if you do the resolution here, you will figure out there's a set of resolutions you can do if H or not A is implied. Yes, correct. Yeah, sorry about that. Wow. Yeah. Right. So this is a bit tricky, but it's quite fun. And all it needs is two 32-bit integers next to each literal. Actually, you can do it with each variable as well. But anyway. Sorry? If I have more binary clauses, well, it can be annoying. What can happen is that something else can imply G. For example, there could be something like X, and there could be something like X or not G. And then you'd have an arrow from X here, let's say, to G. And that would overwrite your little stamping. So you'd forget that H actually implies G. So that can happen. And so, yeah, good point. So what happens is that then you have a partial thing. Of course, everything you have is still correct, right? Everything you have is still correct, but you can't decide you can't always completely decide if something implies something. So what you do is that you run this randomly, okay? You run it with random order of literals that you propagate from, that you start your thing from, your propagation from. And then you have some stamping set up. And then you run your simplification with that stamping set up. And you say, okay, let's forget about this. I'm going to start with another different random order and hope that captures the transitive transitive information that you really want to capture in order to simplify another clause, let's say. Sorry about this H or not A. That's very annoying. Yes. Yeah, so this is actually very cool. I used to do something very wrong, and now this is the right way to do it. Yeah, okay. So I mean, yeah. So this is this ordering of the clauses I already explained. Actually, the funny part from my perspective is that it can actually be expensive just to sort the clauses. So, which is really weird. Like, of course, that's not the case for counting. But if you're actually doing this in the Sat competition, then you might lose because you can do all these things, but like sorting all the clauses can be expensive, which is kind of insane. But yes, so this is actually not used in Kissat or Kadikal, this thing that I just showed, because it's too expensive. It's not worth it, even though it's actually extremely cheap. And of course, it is worth it for many cases. And it's part of Ling-a-Ling. So yeah, an older Sat solver just has it and kept on winning. So it's not like it's a bad idea. Okay. Okay, vivification. Well, this is going to be a bit more involved. We're going to remove the clause from the formula for a moment. We just detach it and hope, and pretend that it doesn't exist. We're going to sort the clause magically, whichever way you want. And we're going to go through the clause one by one, literal by literal. And if the literal is already false, then of course we continue. We don't need this in a new clause, in the simplified clause that we'll eventually create, like a strengthened clause that we're going to create. So that literal is already false. Like, what's the point? So we just continue. If it's true, then of course the clause is already satisfied, right? So we can just remove this clause. There's no point in this clause, having this clause. Okay. So otherwise, what we're going to do is we're going to insert this literal into the new clause, the simplified clause we're going to have, and then queue the negation of this literal and propagate. So we're going to keep on doing this with every single literal and keep queuing the negation of the literal and propagating. And if you think about what we're doing is that we're sort of like trying to see if this clause is already either implied by the formula or parts of the clause can be removed because parts of the clause are already implied by other parts of the clause. So, for example, at literal number n, we have enqueued everything but n, of course, in negated way. So if this nth literal that we're now trying to enqueue is already true, then this must be implied by the formula, and you can remove the original clause. And the negation is but if it's already falsified, so if it's this here, then this clause must be already implied by the formula, which of course means that I can strengthen this. This is just strengthening. This is the same thing that we were doing before. There's a lot of strengthening and subsumption in this talk. I'm sorry about that. This is actually the subsumption, of course, because this is a shorter clause than the previous one, and it's already implied by the formula, so what's the point? And this is this is just a clause that happens to strengthen the clause that we were querying. So, that we happens to be querying. So this is just strengthening and subsumption, but on a clause, literal by literal. I don't know if I've lost half the audience now, but it's kind of, I think it's kind of cool. Yeah, sorry? I do this with all clauses. Yeah, you can do it with all clauses. So this is VB5 for a specific clause, but yes, you run this function for all clauses. This is actually one of the most powerful in-processing systems that is still, of course, used by everyone. But what's more interesting is that this was the only in-processing system that was in Maple, for example, and Maple kept on winning for a long while. So this is really important. And they do this for learned clauses as well. It's quite nice. You can do this, of course, with the original clauses, but you can also do it with the learned clauses. So you can, as you keep on learning new clauses, the formula changes, and that means that when you're rerunning this algorithm, you might be able to remove some literals from the learned clause that you had. So you can strengthen the learned clauses. Like your database can be strengthened as you keep on learning new clauses, and of course the propagation will be stronger, because this thing here is doing quite a lot of heavy lifting. It's of course propagating over the whole formula. So if your formula has changed because you have learned some new facts, that will show up here. Okay, this is the Sharp-Set TD has a thing called Oracle. And they do the same thing, but now they do it with a full Sat solver call. Like forget about propagate. Let's go all the way. Let's actually call a Sat solver. Of course, this is extremely expensive, but the thing is that if you're doing model counting, that's still cheap. So you do exactly the same thing as we did before. You try every single literal if they can be removed, if they're, the clause can be strengthened with, and that's it. Instead of propagate, just call a Sat solver. Like literally, that's all. Next one, sparsification, basically the same thing as the vivification, but here, because you're running a whole Sat solver, you need to do a different call, and all you do is you remove the clause from the formula F, and then you insert the negation of the clause into the formula and say, oh, is it satisfiable? And if it's unsatisfiable, then you know that the formula already implies this clause, so I can just remove it. There's no point in having it. So this can remove one clause from the formula. It's expensive because I'm using a Sat solver literally for every single clause. If there are 10,000 clauses, then I'm going to call a Sat solver 10,000 times. There are some tricks to make this a little faster. You might not need to call it 10,000 times, but yeah, it's quite expensive. But it does remove a lot of clauses, so that's nice. Okay, this is the real trick. So this was 2005, and this is basically what Minisat did really well, and of course Satellite did it before as well. And you can never win a Sat competition with that. This is the one thing you have to have. There's no other way. This and maybe vivification would be nice, but this is like number one thing you have to have. And this is bounded variable elimination. So you say that, well, I want to remove. Oh no, not this one. Oh, the next one. Okay, this one. So what you do is that I want to remove X. I don't like X. I don't want X in my formula. It's a bad variable. I don't like it. So what you're gonna do is you're gonna remove everything where X is there, and you're gonna add all the resolvents of X back into the formula, right? And some of these resolvents happen to be tautologies because there's A or not B. I mean, that's 1 and 4 resolved with each other. If you have a look at 1 and 4, there's A and A or not B. So this is the resolvent here. So this is nothing but we're going to multiply the number of clauses in some sense, because if there are 3 here and 2 on the other side, then it's going to be 6 on the right-hand side, which is what we have here, except that some of them are tautologies. So this is the most important preprocessing you can have. And this is done at a great extent by every Sat solver. And if you have a look at something like KissSat, then Armin wrote a Sat solver inside the Sat solver just to be able to do this better. Okay, I don't know if that makes any sense. Like so KissSat has a solver called Kitten, which is well over 1,000 lines of code that does nothing but trying to do this even better. So this is important. Like you don't write 1,000 lines of code just for fun. Like this is really, really important. Okay, so now, yes,
Just the original VP algorithm.
yes,
but
exactly.
you don't want to do this all the time.
No, you don't, because it can explode. Yes, so there are two things to do here. One of them, so the explosion thing that we're talking about is that if you do DP, so the Davis-Putnam algorithm, what it does is that it just removes variables one by one, right? And eventually the problem is that things explode because here we have 3 times 2, which is 6, which is nice. But if it's like 100 and 100, then it's 10,000. So I remove 200 clauses and I insert 10,000 clauses in. So that's a bit of a problem. And 100 by 100 is not even that much. It could be 1,000 by 1,000. So you remove 2,000 variables and you add a million. You remove one variable, you remove 2,000 clauses, and you add a million clauses back in. So this can explode very quickly. The reason why it doesn't explode is partially, I'll explain a little bit, but Kitten was written specifically so it doesn't explode as much. Of course, at one point you have to stop. The trick is that you only do it in case you get less resolvents. That was the original idea. Nowadays, we actually allow a certain amount of what they call a growth factor. So we still allow it if it grows by a small amount, like you, for example, remove 6 and you add 8, or you remove 10 and you add like 14. Like we still allow that. But eventually, of course, this will explode. So you have to be careful. The other thing is like which order do you do this, right? Because it makes a big difference which order you do it. We actually use a very simple heuristic, and maybe Tuka and so this Oracle tool that I was talking about uses actually a graph-based system for figuring out which order to use, which is quite cool, I think. But let's get back to this for just one moment of like, how do you make sure that you have as many tautological resolvents as possible? Because that's what you're looking for, right? Because if you can remove 10 clauses and insert 0 back, I mean, that's kind of nice. So the question is, how do you make that thing disappear? Like those things, do we really need all of those? And first of all, we can do this weakening. Remember the weakening where you can add the literals to a clause? Well, if I can add the literal to this clause, for example, and with not D in there, well, then this becomes tautological. So what you do is that you take these clauses that are here on the left, you weaken them as much as possible, then you do the resolution and check whether they drop out. Because if you weaken them, like you add literals to them. But if you add all these literals to them, they might disappear. If they disappear, that's good, because now you can remove this one more variable. So that's weakening. Then you can do, of course, subsumption. What you can do is that you take these clauses here and like, okay, I really need to add them. That's very sad. However, A or B might subsume some clauses in the original formula. If they do, then actually I kind of add one, but I remove some others. If they all add up to be less than the original set of clauses, then I'm happy. So you can do subsumption on these. And of course, we do subsumption on all of these. You can do this parsification that I talked about. So you can remove some clauses using like actually a set solver just to remove like some of these clauses that are here. So that's kind of an expensive check, but you can do it. And then you can make sure that, when you do the resolution, you don't have to add those. Okay, strengthening is kind of annoying, but what you can do, of course, strengthening is exactly the opposite of weakening. So now you're in a bind because, what do you want to do? Do you want to weaken or do you want to strengthen? Like it's kind of unclear. So what you can do though, is that what can happen is that these clauses here on the right happen to be binary. Well, binary clauses often strengthen quite easily because all you need is one literal and the other one negated in a clause for me to be able to remove a literal from a clause. So what you can do is you can strengthen in these things. It strengthens some clauses, and now you can use those clauses to subsume other clauses because now they're strengthened, they're shorter. So there's a chance that they actually now subsume things that previously they couldn't subsume. I mean, of course, there's quite a lot of, like, you can do this to the next level and next level, and then the question is, how far do you go and what do you actually do? Same thing with vivification, same thing with like vivification that is using this Oracle tool, which is to strengthen it even further using an actual Sat solver. Okay, there's one more trick. For this bounded value elimination. We can do it on gates. So let's try what happens when this is just x equals a and b. This is the gate. And if you have a look at the right, it just disappears. There's nowhere to be found. Goodbye. Well, the nice thing about this is that this is not accidental. If you do a bounded value elimination on gates, and there are other clauses as well, then you're guaranteed that some of these things disappear. And What's nice is that there's one more thing that happened here, which is kind of weird, because remember these two clauses that disappeared? Well, we expected them to disappear, right? Because this is just the same thing as above, except that it has two extra clauses here. You see these two extra clauses that I added just to mess with this. So I was expecting these two to drop out, but somehow D or C also dropped out. And of course, why would it drop out? I mean, this is not a tautological clause if you look at it. Well, the reason why it dropped out is that you can actually reconstruct this D or C given this here. You see, you can resolve D or not A or not B with A or C, which is here. And then you resolve that with B or C, and then you get D or C. So D or C is actually not needed. It's already implied by these three clauses. So this fourth clause is redundant. So this happens to be a rule. This is not accidental. And so let's call the gate part the gate part, and the non-gate part is other. Okay, I'm just calling it other positive, other negative. You see gate positive, gate negative. Well, it turns out that you only need to add the gate. Of course, the gate resolve with the gate is always tautological. We know that. So you don't that economically drops out. But also the other negative, the other positive is not needed. So that's also drops out. And now you end up with this, which means that you have less resolvents to do. This is not always true. It's true for AND or and XOR gates and the equivalence relations, but it's not true for example, if then else gates, and it's also not true for irredundant gates. But a lot of the gates you're going to find are these AND gates, because a lot of the work that we do, the problem that we're working with are a bunch of electronic circuits, so there's quite a lot of AND gates and OR gates. Yeah, also true for XOR gates actually. Yeah, you have to. You actually have to read the paper. That's I don't have a simple answer on this. I'm sorry. I wish I did. One more thing to say is that you can actually do this. So that's kind of annoying again. But anyway, you can do a resolution and then subsumption, which is just the trick. What you do is that you see, for example, this thing here, which is very closely. This is closely related to bounded variable elimination. What you see is that, well, there are other x's all over the place. So it's just, but this, I'm just going to have a look at this for the moment. And I see that if I resolve these two clauses with each other, I get the third clause. So there's no point in having the third clause. I can just remove that. Right? So I can always reconstruct this clause, of course, from the original two. So you can do this kind of resolve and subsume, which can remove some clauses. The only problem is if you do this, then your heuristic here will be messed up, because it might remove some clauses, which this would remove as well, and etc. So it's kind of annoying, but yeah. Okay, so here are the different gates that you can, if you really want to feast your eyes on these variable formulas, but that's just a description of the different gates. I think so this is the end. You can ask me questions. I think I've already exercised your mind maybe a bit too much. There's one more thing. So these are the different gates. Of course, these are things that all of us know. And you can also have something called irregular gates. And this is what Kitten, this Sat solver that I talked about, does inside KISSAT. Irregular gate. So irregular gate is basically what it says is that it's a bunch of clauses, and they together always define X. Like in one way or another, they somehow always define X. And of course, these all define X, right? They all define X in very clear, easy ways. But there could be other set of clauses that also fully define X in a, that has a different truth table. And if that's the case, then it is still a gate. And if it's still a gate, then you can do some of these simplifications. In particular, the gate doesn't need to be crossed with the gate, etc. So this really helps with bounded variable elimination. And that's how we get to the level of simplification that you saw. I think it's very important, yes?
So, can you tell us something more about the ordering heuristics and how do people figure out?
Yeah. So, okay, one thing, the question is very good, but it's very hard because we use the simplest thing you can possibly imagine, which is quite funny. So one thing that is the trick is that you need to have a heap data structure, because as you keep on removing clauses and adding clauses back in, of course, you might change the formula itself. And if your ordering depends on the formula, then the ordering needs to change. So it needs to be not like, oh, I compute one order and now I'm going to run through this order in one way, because the moment you eliminated the first variable, your order is completely wrong already, right? Okay. So they use a heap data structure for this reason. And actually, the way they count is they count the number of occurrences of X and the number of occurrences of not X, and you multiply the two together, you get some magic number, let's say 6. And if this magic number is low, then you eliminate that first. Which makes a lot of sense, right? It does make a lot of sense. But I mean, another thing you could do is that you actually simulate the bounded variable elimination for each and every variable, like all the 10,000, which can be very, very expensive. And then you pick the cheapest, which still wouldn't be like the perfect order, but it's at least not like it's slightly more smart, you know? No, too expensive. It could be actually useful for something like counting where you have more time, but not when you get a formula, it has like, I don't know, 1 million variables. This thing can remove a lot of variables. Like if you ever look at KISSAT, just start up KISSAT, it starts with some large thing. And then like I don't know if you have seen like all number of unknown variables. And it's like 2 orders of magnitude smaller than what it started with. And you're like, what is going on? Like, why? Like why does it have so much fewer variables? And well, that's why. Because it does this BV immediately. And like 2 orders of magnitude is not even a big deal. Like, what did we have here? 142. What was it? Yeah, so we started with 7,000 and ended up with 387. So we did like a bit more than an order of magnitude. For this really large SAT instance, this is counting. Okay, if you want to do like a SAT instance, 2 orders of magnitude, not a big deal. But I mean, we can never count those, so. So I didn't even run it through this. This tool is quite expensive. I mean, 12 seconds, okay, but still, relatively speaking, it's quite expensive. So this is the tool running. I mean, I can also just not do this, and then you might be able to see some output. Okay, so this is now doing backbone, right? Then it's going, what is it doing? So it's a ternary resolvent, variable replacement. So this is the strongly connected component. It discovered 6, it replaced it. And then it did it again. The reason for you to do this again, which is kind of strange, like why would you do that, is because if you remember the thing I was talking about here is this thing, if you have a loop, you're going to have problems. So you can't have a loop. So after, like, you have to make sure there's absolutely sure that there's no strongly connected component. So I do one more analysis of strongly connected component just in case. Because I mean that was one, so and I changed. Oh, sorry, and I changed the problem. And then I call it distillation, but it's the same as vivification. So we tried 5,000 closes to be distilled, and nothing happened. I think we can go up, and then you might be able to see some that actually does happen. So no closes were removed. Or no closes. No, that's kind of annoying. Nothing got shortened. So oh yeah, nothing. Oh, I know why nothing got shortened, because that's okay. So here, for example, this is this vivification. You can call it distillation. It's very similar, very related. I tried to try it on 10,000 closes, and I managed to remove 2 closes with it. Yeah, that's how it works. This is okay. This is more backbone, and I don't know what this is. The sparsification. So this is Oracle, this tool from Sat+Smt, and it removes 3,300 closes because they all imply by the formula. Of course, the order in which you do it is also very important, right? Because it could, like, if you remove at the very beginning some really important close that would otherwise remove many others, then bad luck. So that's still a problem. And I think I still also do vivification at one point. So. Yeah, I want to see if there is anything more. So this is the entry. Yeah, so this is the transitive reduction. So we remove 2 binary clauses that are irregular. So this is this transitive reduction that I talked about. That A implies B and B implies C, and then the question like, is there a clause that says A is inclined to C? If there is, I can just remove it. There's no point in having it. Right, and here's the variable elimination, by the way. So we started in this round, we started with that many. We tried to eliminate more than there were because we do it more than once in increasing fashion of strength. And then we remove 52, so below this. It starts, like we can actually check the, if you want to, I mean, maybe this is not that exciting for all of you, but we can try to see where it really, so here, like on the first round, it removed 3,000 just off the bat. I don't know if there's any more. Yeah. No, that's another execution of this. Yeah. So yeah. Yeah, 3.0 second to remove 3,200 variables. Yes. I mean, and this is also doing weakening in the background and subsumption and all that sort of stuff. So it's not just right. Yeah. So here's when I do. I actually use Picosat to do this irregular gate detection to make my life a little easier. and that helps as well. To remove the number, like shorten, make the number of resolvents smaller, so therefore shorten, hopefully less than what we started with. Okay, I mean, this is kind of annoying probably to all of you, so I'm not gonna go any more. Any questions? Yes. Not similar. It's a very specific ordering. So the starting stamp needs to be smaller, and the ending stamp needs to be also smaller. So, so 17, 18. You see the 17, 28. You see here. This is, so the question is like how do these things work? So in terms of like how do you know what implies what? And this is 17. This is 28. And this is 22 and 23. So this both of this basically is contained within this. So you know that there is a clause that says H or not A. Yes. So yeah, this you can actually read. This is called the parenthesis theorem. You can look up. I mean, you can also look up the paper that this is from, but the original idea is not theirs. It's actually this parenthesis theorem. So it's contained within it. You can think of it as intervals, and if the interval is fully contained, then you're good. So this is an interval of 22 to 23, and it's fully contained in the interval of 17 to 28. So therefore, it is implied. Right, but it's a constant check once you have done it once. So once you have done the depth first search once, then it's a constant check. I mean, constant to less than operations. So it's quite nice. Nice trick. Yes. Somebody else. Yes. Not this one. So good point. And the question is, will the Sat? So let's say that this one, I remove this clause. Remember that I removed this clause. This can be used to remove that clause, right? Same thing, basically. It's just this is a more advanced version of that. So let's say that I remove this clause. Well, the Sat solver can be like, well, I really need that clause. Well, would it? That's the real question. And the answer is no, because these are all binary clauses. The binary clauses are always very special. And the software will always figure this out, because when it propagates either of these things, it will always be implied. So it doesn't need to do that. It would be true for longer than two long clauses, but two long clauses are special and it's not true. So you can always, and you definitely want to do transitive reduction, or this is called transitive reduction. Yeah, it does say transitive reduction. That's good. So this is transitive, and you always want to do it because it's just in the way. It's just making your watch list longer. Doesn't help in any way. Well, okay, it only helps if you want to subsume with A or C, and it's not obvious to you that A or C is not implied by these two clauses, right? So if these two clauses obviously imply A or C, and if you want to do subsumption with A or C, then that might not be obvious. But the thing is, then you just do stamping, and now it's obvious. So we do quite a lot of forgetting and recovering. But in terms of propagation, and instead of like what you asked CDCL, for CDCL, this clause here is useless for CDCL. For if you want to do pre-processing, now you need to recover it somehow because you just forgot it. Yeah. You can even have like a separate database of things you forgot and then strengthen with all that. And you can have fancy things. I used to have fancy things, but I reduced it's only 50,000 lines of code now, okay? I don't have, I'm trying to compress. But you can do that actually, yes. Yes? Yes, I think for these things, it will never be learned because, yeah, never be learned. Except for, I think for weakening you can, but I never weaken the clause unless I do bounded variable elimination because I mean, that's the only reason why I would ever weaken a clause. I always want to strengthen it. So yeah, that is true, correct. But the thing is CDCL cannot, for example, simulate subsumption at all. I mean, half of the things that I was talking about is subsumption, right? So CDCL will never do that. So this is what I meant by CDCL is quite weak, actually. Yeah, but this bounded variable elimination, of course, it can do. Like, it can do all these resolvents. It will generate all these resolvents. It just won't remove, like, won't realize that I can remove all these things if I did all these resolvents. Like, it can add all these resolvents as part of its search-directed proof generation, but it will not realize that these can be removed. You can do some kind of expensive check and check if, you can really remove it, but yeah.
Question more about your
Oh, sorry.
You're losing lots of clauses. Could any of those affect?
Yes. So the one thing that is very true is that this boundary elimination can be a big problem. So what it can do is that, so there are some, for example, the pigeonhole formulas, you can actually add extra variables. And if you use these extra variables, then you can have a much shorter proof. But now with boundary elimination, you can actually accidentally remove all these clauses that would have helped you, and you now have an exponential proof. So you can get way worse, like exponentially worse than before. Very sad. But structured bounded variable addition, which is the thing that won this year, the competition, which is the reverse of what I'm telling you is the best thing that was ever existed, is the one that won the competition. But the way they do it, of course, is they're smart. What they see is that, of course, this is reverse. So they're gonna just think about a switcheroo. So the thing on the right is the one that gets that gets removed, and the one on the left is the one that gets added. But the trick is, of course, you want it to get smaller, right? So you still want the set of clauses you want to add is smaller than the set of clauses you started with, so you can get smaller. But just because the structured bounded addition, it doesn't mean that it will not destroy this thing with the PHP formula, for example. So you're hoping that it will help, but we still don't, we can't, we're hoping that it will help. But yeah, so it's quite funny that the structured boundary variable addition is the one that won this year, and that's exactly the reverse of what I was telling you is the best thing ever. But they still do boundary variable elimination, just to be clear. So they of course run everything all the way to fixed point with this thing, well, fixed point all the way they could, and then eventually they run this structured boundary addition to do it reverse. And sometimes what will happen is, and it's very, very annoying. So you add back you add the new variables, so you reverse what is written on this slide, and then of course you solve the problem, and eventually it turns out that it's best if you eliminate the thing you just added. So eventually you go back to where you started, hopefully not worse than where you started. So there's quite a lot of tricks, but don't worry about it so much. Just so this is good enough. Like it's pretty good. We've been running like this for a long time, and it's been good. So it's not like structured. And I also have BVA, so not structured BVA, but BVA in my tool. So I can add variables, and I do add variables if I want to. But SBVA is like more cool and better. It is better by quite a bit. Yes, of course. Yes. Yeah, exactly. Subsumption, strengthening, like all this kind of hyperbinary resolution. Literally, this is dicey, but at the same time, this is the thing that gets you there. Like I can show you what happens if I turn off bounded variable elimination, and it's going to be like, instead of 7,000, we're going to have 6,000, not 300 and whatever. So it's going to be a very different ball game. So we need it. There's no way of not using it. Like if you don't use it, you're stuck. Oh, okay, I don't have the. Oh yeah, I do. Counts. There we go. And simp. Right. So you're gonna. I mean, I can try to run it without boundary elimination. I'm not even sure that's possible, but we can try. Yeah. Yes.
Yeah. Okay. It was a great discussion. Thank you, Mate, for a really great talk. And we can break for tea. So it's the same place as we have been having it last 2 days. So come back
Sorry?
at 10.
Yes. It was sleeping. Oh.
So we'll come back at 11:10. 20 minutes.
Thanks, replied, I'm scared. But then my word okay.
These lights are required. Lights are coming on nice. Usually it's supposed to be dark. Um, I don't know. Yeah. Oh, okay. Okay. So should I wait? Mhm. These lights are correct. These lights required for the streaming, is it? Okay. I, it's okay, otherwise I can manage. Anyway, no problem. Should I wait? Mm-hmm. Sure.
I know. Yeah, I think we should. Yeah, I think we can start. We are at 11:13, 3 minutes past. Okay, so welcome back, everyone, after the coffee break. So in this session, we'll have 4 short talks that would spur longer talks during the lunch break and afterwards. So our first speaker is Dr. Sangaratna Godbole, who's faculty at NIT Warangal. He's going to talk to us about an extensive investigation of condition reachability using CBMC. Over to you.
Thank you very much. Is it audible?
No, I don't think so.
Hello.
We can fix this if you want.
This-
Keep- Oh,
I can use my mic as well.
you have a problem. Problem.
Yeah.
Yeah. Oh, you have your.
Am I audible? Am I audible? Yeah.
Just for the online recording, is there an online recording happening? Is there a Zoom recording happening?
I think this morning also we didn't.
Live.
We didn't have? Huh?
There's a light.
There's a live YouTube going on. Is it the sound should be okay, right?
Hello, 1, 2, 3, 1, 2, 3.
Maybe. Okay.
Hello. Yeah, fine. Very good morning, everyone. Thanks to organizer. And my topic is an extensive investigation of condition reachability using CBMC, study on negative results. I'm Sangaratna Godbole. You can call me Sangu. I am an assistant professor in NIT Warangal. Also, I founded my startup, that is NIT Minor Technologies, which is powered by Computer Science Department NIT Warangal and funded by Government of India. Uh, um, so this work is funded by my own startup. So this is the outline, introduction, motivational examples, some experimental results, and then conclusion. So I can see like Sat+Smt workshop, people are here core with the satisfiability domain, right? So I was just talking to Subhajit, right? Okay, we are software testing people and we definitely using this Sat+Smt. Okay, so we are on applied side and for the Sat+Smt. So as you can see here, for software testing, so we have two different modes, bug finding as well as the coverage. And when we go to, let's say, structural coverage, we have some important criteria. For example, statement coverage, condition coverage, modified condition decision coverage, and CDC, multiple condition coverage for the source code. Okay. So for MCDC, as per the airborne systems, to achieve a level A certificate, as per document DO100 B and C, MCDC is required. Okay. So, and for levels B, C, D, E, these are the categories of the softwares where the condition coverage is also required. So it means that it is important whatever the report you are actually giving to the developers, right? So based on the coverage value, you are going to approve the application. So it seems to be very important to report the coverage. So CBMC is a state-of-art tool for bounded model checking and widely used in, let's say, like industry as well as the open source way, right? And what I have actually investigated, since I was also using CBMCs during my postdoc as well as my research since 6 years, I'm using it, and I found some issues in that. So, well, this talk is not to this work is not to criticize CBMC, but just to give some alarm that okay, if we are relying on some code coverage, we have to be little careful. That is what the main idea behind this talk. I experimented for almost 1100 plus C programs taken from different domains and reported that 909 programs have some issues. Okay, issues means I will tell you shortly what are the issues. And it's like almost 80% programs having issues. So I have taken motivational example. So this is my first example and we will be playing with this only. And I'll show you how exactly CBMC is acting on this. So as you can see, this program is very small, artificially made. And there are three variables, A, B, C. And you can see B is concretized to, let's say, initialize with 1. And there are two symbolic variables, A and C. So when we say symbolic, so of course, we require to achieve both the branch edges. Now, the two predicates here, like A is greater than 5. Inside that, you have another predicate that is B equal to 0 and C is greater than 90. Very small program. The logic is if A is greater than 5, then and only you are able to reach at line number 9, which is B equal to 0 and C is greater than 90. Okay. The first one is a predicate as well as it is atomic condition because the if statement is only having one condition. But in the next predicate, it is like, composite of the conditions. There are two atomic conditions there, B equal to 0 and C is greater than 90. So there is a conjunction of both the conditions with the AND operator. Now I just want to like bring you there in the short circuiting logic. What happens in case the first condition is true, then and only C is greater than 90 supposed to be evaluated, right? But if it is false, B is equal to 0 is false, then C is greater than 90 should not be evaluated. Evaluated in the sense that it's supposed not to give you some kind of satisfiability result or some solution for that. If it is giving, then it is counted as covered, which supposed not to be covered actually. Okay, so we are expecting that there are 6 branch edges, and the first branch edge may give you, let's say, true and false branches covered. For the b equal to 0, you can see b is equal to 1 already initialized. It means the true branch of b is equal to 0 is always false. Okay, and b equal to 0, false branch will be satisfied. Okay, that we are expecting, and we are not expecting anything satisfiability point of view for c is greater than 90. So the thing is, when we play with CBMC, so we get this result. So as you can see, for the first one, it is satisfied. It means it is covered and giving some solution for that. When it comes to b is equal to 0, false, b is equal to true, fail, it is giving you correct result, because we know that b is equal to true branch is not correct, means that is not satisfiable. So it is saying failed. Okay, and b equal to 0, false, it satisfied. But the problem is that c is greater than 90, false, and c is greater than 90, true. It is giving you satisfied result. It means it is reached and giving some solution for that, which we don't expect actually. So just I want to play with it, and I will change something, and we can see the results are. So I'm taking this program as it is, as we can see here. So if you are aware about CBMC tool, it gives you coverage, and this is the command to run the CBMC. As you can see, okay, it's supposed to be, I'm taking the program dead.c, the program name is dead, and there is one option, cover, which have some different coverage criteria. For example, condition coverage, condition decision coverage, as well as MCDC. MCDC seems to be the strongest one. So we are taking MCDC so that all weaker coverage criteria can be covered. And it gives all kind of coverage values. Unwind tree, it depends on the loop bound. So just you can give, either you can remove or you can give any value here, because program is loop free program. And this is just for the timestamp. So we have run here. You can see the properties here. Properties with its solution, whether it is satisfied or failed. So I just ask you to ignore the MCDC independence, just ignore that, because we are not focusing on that. We are focusing on the condition reachability. So for the first one, if you have a predicate, itself is a decision and itself is a condition. So coverage is your, let's say, decision condition coverage. So it's okay. A is greater than 5, you will get satisfied. And for false body also, it is satisfied. You come to this part, the last 4, let's say, properties. Here you can see that C is greater than 90 and C is greater than 90. It gives you the satisfied, let's say, solution. And B is equal to 0 is satisfied. B is equal to 0, true, is fail. Means what we are expecting. But we are not expecting C is greater than 90, false and true, both supposed to be satisfied. Okay. Now the magic is here. Like what I do, I'll just change the, let's say, without logical operator, because my main target is to focus on that CBMC is not giving correct result for the program with Boolean expressions. So if it uses logical operators, then it is not giving a good result. That's what my target is. So I just want to make it simplified one. If we do simplification in this way, as you can see, so it is just syntactically different, but semantically same. Because what happens if A is greater than 5 is true, then only it will come to the, sorry, B is equal to 0 is true, then only it will come to C is greater than 90, and it checks whether it is true and false for both the branch edges. I'll run the same program again. You can see here, and we will just focus on this properties. The results are different now. Here you can see that C is greater than 90, C is greater than 90 is giving you, let's say, failed, let's say, property. It means it is truly unreachable, okay, because of the B equal to 0 condition, okay. I'm assuming and I'm considering this result is correct. Okay. So if we don't use the AND operator, then it is giving you correct result. Okay. And we have, let's say, several transformers like CIL, you can transform the program. And also if we use Clang compiler, and if we convert the source code to the LLM intermediate language, and everything is coming to your atomic basis only, then you may get some good result. But CBMC is directly running on the source code. And if we rely on the source code, then such ambiguities may come. I have another version of the same program, as you can see here. My problem was the condition is dead, then such problem fails come, right? Here what I did, I changed the value of B. It was 1 earlier, now it made it alive, like B is equal to 0. Now you can see that B equal to 0 is always true, and the false branch is, let's say, not correct, okay? And if it is always true, then there is a chance of computing C is greater than 90, okay? Whether it will be satisfiable or unsatisfiable, okay? So we will see now what kind of result we are getting. So if I run a live program, it gives you correct result. For example, focus on this one only. So B equal to 0, false is of course false, and B is equal to 0, true branch is satisfied, which is correct because we intentionally made it. And after that, C is greater than 90 is satisfied, okay, because it is symbolic and it is giving you the solution for that, okay. So truly, if the condition is reachable, then it is giving you some correct result, and if it is not reachable, then there is a problem. That's what actually am I trying to tell. Even when we simplify this alive program, okay, just to cross verify that if the dead condition that we actually played, whether it was correct or not, it will give you same result. It will give you same result. You can see both the properties are correct. Now here is decision and condition both are in atomic, so it's same coverage, and you can see it is satisfied, and B is equal to 0, false is failed, and B is equal to 0, true is satisfied. Okay, that is what the idea behind this. So well, I showed you that demonstration, whatever reported here. So I experimented with the let's say almost 1100 programs, as I said, and those programs I have taken from these sources, and also some of the programs from big set of programs from SVCom, where CBMC as well as other tools are participating for the challenges. These are the commands that I use, so that I just want to make sure that I'm not making any mistake in the syntax. So I'm using seal, and seal has both the options. The first one is use logical operator, don't remove and don't convert it, don't transform the program. And based on that, I just want to play, that is the mode 1. The second command says the mode 2, where I don't use logical operator. By default, seal is transforming to the version where you have everything to the atomic condition. Okay, and this is the command that I use for the CBMC to cover MCDC test cases. And these are the results. So what we expect, that if we have the program with logical operator or without logical operator, because semantically both are same. So we expect the coverage supposed to be also same. Okay, so as you can see here, uh, blue dot says reach original, it means with logical operators, and reach simp, it says without logical operator, means simplified one. And you can see we are expecting both coverage supposed to be same, but it is not. You can see clearly there are some differences. Blue and red dots have some differences. It means the coverage coverage metrics are different. Okay, and if we let's say consolidate in the table for 143 programs, we got 353 coverage report for 353 programs same. For 783 program, which is quite huge, more coverage, and for one program we got the less coverage. And as I have given 300 seconds as a timeout for CBMC, so we were short of time, and we have given just 6 program for timeout. And different scenarios in total condition, that was the situation, and different coverage scenarios if we take. So we were, let's say, lesser in the 909 programs. We got equal in 213 programs, and wrong reports that actually we are getting because of the report, it is for 21. So total 1,143 programs we played, and we found the problem in almost 80% of the program. Okay. So, well, that was my thought, and this is funded by the DST, Government of India, for my startup, and through that I'm working here. Okay, questions? So just a disclaimer, it is not criticizing to CBMC. I just want to aware our society that if we are using, because of course CBMC is open source, but still it is being used in several industry. And if we directly rely on the coverage, then it's a problem. So I just want to make sure that, okay, just cross verify with other tools as well, and just be confirmed before going ahead. That's the point.
I think that's
Yeah,
well
and
taken
any
care of.
questions?
Does what it saying, it's supposed to do, right? Basically, the thing is that the composite condition, I mean, if you look at the go to IR that it generates, so it has an intermediate representation. And if you look at the code that gets emitted in CBMC, and you would see that basically, because see this short circuiting thing, I'm not aware if somebody has read the C standard and whether that is something mandatory on the compiler. That is something compiler probably does.
It is.
Right? So if, for example, so CBMC is trying to remain faithful to the C standard, not to like some compiler optimization or something. And that's why if you see the composite condition in the IR, it is expressed as one composite, basically logical predicate. When you break it up, simplify, obviously now, as per the rules of C program, it has to follow that. So CBMC does exactly what it claims it is doing.
True, but if I'm a user of, let's say, CBMC, so if I'm expecting that some coverage output, let's say for condition coverage, of course, atomic condition is sufficient, but when you go for MCDC, then Boolean expressions are important. Okay, so short circuiting will come into the picture. Okay, and if it is not following short circuiting, that is what my point is. Whether it is, yeah, Subhajit.
So I think the whatever you rewrote is as per what short circuiting would have done.
Correct, correct.
I think the one issue that I see, otherwise pretty interesting, but one thing I see is that the two programs you cannot cover, you cannot talk about their coverage because they are different programs. They are different programs because their coverage metrics are so. So the denominator of the coverage is different. In the first case, like if you're doing MCDC, when you have the AND, then you have your denominator would be 6 because you are trying to get both sides of the branch and both sides of each predicate. So the denominator would be 6. But when you break it up, then the denominator becomes 8. So it is not surprising that the first one gets you less coverage because the denominator is
No. Subhajit,
sorry, the other way around. The second one gives you more
No,
coverage.
I'm not relying on this percentage, by the way.
Acha.
I'm not relying on this percentage. I'm relying on particular property. That's why I shaded it. You see, C is greater than, C is greater than 90.
But you will not even get these things in the first case because if you go by MCDC for the logical expression, then you have six metrics where you make each decision true and false, and for each predicate you make it true and false. So you will not even see these 8 conditions that you are expecting.
It will. No. What I'm trying to say that I'm not focusing on MCDC requirement. In MCDC, condition coverage is also essential, right?
if I use, okay, if I use instead of MCDC, just condition, okay, that is also one metric. Okay, you will get different result. What I'm
Yeah, but again, the denominator is different because in the first case that you have broken it up into two branches. So there are four, the denominator is at 4. In the second case, when they are together, denominator is 2. So these are different programs and coverage is very syntactic. So it goes by.
Keep B undefined and then see what happens. So you keep B undefined. Let's say it's a non-deterministic int, and then you should see that whether CBMC is giving you the inputs for each of them individually. The
So-
thing is that when you define it, I mean, it does not matter what the value of C is. Even from the rule of basically you have fixed that constant. In fact, the compiler from the like constant propagation itself is going to simplify this.
True. For Subhajit, let's say point, let's say if we are in this format, so how many branch edges are there? 6, right?
4 coverage
4 condition coverage,
for the first two, for
and including this one.
I'm talking about only line 11 and line.
Okay, correct. Line 14 and line 16, right?
Okay, the logical was there, 14 and 16. Yeah,
Yeah,
So,
correct.
irrespective of it.
Yeah. Now here, if I just cut it, and now how many denominator? 4.
6.
No, for this one.
Again, line 6. 2 for the decision on 14.
I'm not talking about decision at the moment. I'm talking about only condition coverage.
Condition coverage.
4, right?
No, just a, so condition coverage or decision coverage?
Only condition. Exactly.
Yes.
So I'm not talking on MCDC, not decision, only condition. Okay,
MCDC is 6, decision is 2, condition is 4.
correct. Now, if I keep it down here, how many conditions?
4, right?
Exactly. Condition coverage for with predicate or without predicate, only 4.
No, see,
Yeah,
I think,
I'm focusing on that only.
see, it can statically prove that basically this is never B is equal to 0 is never going to be satisfied. You make B as non-dat int and then you see, only then it makes sense. I think you have misinterpreted what CBMC is supposed to do. You
Uh,
make B as non-dat.
I agree, but in
And
real,
then you can throw as many composite condition to CBMC. For each individual case, it's going to actually find that this part of this composite condition is false, and for this it is true and whatnot. By saying that B is not a non-deterministic int but is a 1, this is something that even compiler would be able to simplify. CBMC is not violating the whatever the semantics, etc. I think that you have misinterpreted what CBMC is supposed to do over here. Make B is equal to non-dat, right? Only then, if then CBMC fails to give you the coverage like input for covering of each of that, then only that claim is true that CBMC is not doing correct thing. With you fixing value of B, I think that you have misinterpreted what it is supposed to do.
okay. Offline, yeah.
Okay,
Okay.
I think that was interesting discussion and interesting talk. I
Thank
think
you.
because CBMC is used quite a bit. I mean, for example, thesis research, definitely we use a lot of CBMC. So to have these observations, I think it's very useful. So we can have some more discussion after the talk.
Sure.
Okay, so
Maybe
thanks.
we'll take offline.
Yes, certainly. Thanks for the nice talk. Okay, our next, sorry. Yeah, I think next speaker is Sushim Srivastava from Qualcomm. Wow. Just yes, next speaker is Sushim Srivastava from Qualcomm. Qualcomm is indeed a sponsor for the event, so I think the presence is very valuable. And he's going to talk about on a very interesting, very short talk, but a very interesting theme about mathematical foundations in computer science from the perspective of the industry. So looking forward. Actually, rant, not a talk. This thing. Am I audible? No, not really. Hi. Yeah. Now? So actually, I was supposed to present something else. Then I met Shubhajit on Friday, right? Yeah. We met on Friday, and then there was a rant. So I said, why shouldn't I rant here? So there's a long rant, so I'll try to cover in 10 minutes. So in a way, I'm upset over industry. The rant is about what industry is doing for mathematical foundations computer science, right? Starting from, like in India, if you go for ICBGIP sponsorship, there will probably everyone standing there to give out money. And once you come to any mathematical foundation conference, there's a struggle to get the money. Not only that money part, but I want to dwell with a little bit deeper into getting students for the master's courses or the PhD candidates for all the mathematical foundation courses or systems courses. So ideally, if you take a look at how computer science should be taught, if you look at a pyramid, so it should be like, pyramid should be like this, and bottom there should be mathematical foundations, then there should be systems, and then there is applications. Now what happens is people are, this placements or the job, what happening is because of this. And probably the pyramid is, this much pyramid is only remaining this, they just want to pass the courses. So we tried something with, like, I lead compiler design team in Qualcomm. We tried something with compilers for last few years. And this session is more about our taking a feedback from people. And if other folks in this team can do a similar thing for other topics, because I understand compiler, that's why I did it. So 7 years back, we started compilers team in Qualcomm India. And that year, I sent out an email to all the IITs, all the IIT professors who are teaching compiler design. And there were 2 candidates from the grad students across all IITs and ISCs who have done project in compilers, which was a very minuscule number. So then we started speaking about our work at different institute. Like we started with the grad level talks we did at IIT Kanpur with Shubhajit. We spoke about Superblock scheduler and other things. Then we spoke at IIT Madras about, again, a grad level work. But grad level student is already doing compilers, right? So I'm preaching to the choir that this is important, right? So then a suggestion came in from these sessions that why don't we connect a systems engineering course compiler design to the end product? How it is making, like how compiler is making ML happen, how compiler is making, AI happen. So that's how we started our first course. Again, we did with, first time we presented at IIT Kanpur at ACM Winter School, Industry Perspective on Compiler Design. It went pretty well. And then we did it here rather in IIT Hyderabad and IIT Hyderabad. Every time compiler course starts, the first lecture we are doing right now, that how compiler is enabling the end product AI, ML, and other technologies. Then we got another feedback because it was just very basic. We were adding up. Then they said, can you, and these were like no prerequisite presentation, a second year undergrad, even a first year undergrad can understand. So then we were asked, can we add for compiler design optimizations, which are very proof oriented, without proof, intuitive, which an undergrad second year or first year can understand. And then we added that part. So we are doing this for last 3-4 years where it has evolved. Then we started adding something on computer organization side, because computer organization mostly taught around x86 and little bit on ARM. So we started showing how microcontrollers, accelerators, DSPs are important, again, as part of the series, and how domain-specific languages in conjunction with like how programming languages is enabling all these technologies. So this whole basket kept getting evolved. So that's a little bit of good part of it. One good thing we have seen is we posted on social media, if you want to make career in compiler design, do this and we'll interview you. And we thought, okay, it's a futile effort. Last year we got 2 emails. I have done all the things which you have listed here, and I am ready for interview. Will you interview me? And by the way, your 2 links are wrong. Now they have moved. So can you correct it on your presentation? So these things work, may not be in that level. So this is a good success story which I was talking about. Now, what I am expecting from the industry or academia or students here, suggestions and help on preparing a similar connect between other subjects, probably a theory of computation and algorithms and the end product. Like it's onus on the industry more that because academia's job is to provide with the theories, proofs, and the academic stuff. But how it is connected to end product, that's industry's job, which we are failing in doing it. Because if industry and academia don't do this together, this is not going anywhere. So my rant is about, this is the summary of rant. I can go around with examples and examples and examples. Like I can show this, that. Like right now you talk about one chip out here, which does all a lot of stuff. But in one chip, there are like hundreds of processors right there inside. There is one CPU. There are 7, 8 different DSPs whose instruction sets are different. Not 7, 8 are similar DSPs. Close to 100 plus microcontrollers. And everything in different instruction set need to be optimized for power optimization to memory optimization. The buses need not, get choked. The latencies needs to be maintained. And all these analysis is possible if we are able to have good candidates coming out to be with a good background in systems and mathematical foundations. Because okay, here I can give an example. So we had one optimization, we had one actually hardware issue, or you can say trade-off. We removed some block. Because of that, one memory cycle was additionally consumed when the chip came on the block. One memory cycle was additionally consumed in load cycle. Then we had to do some optimization in compiler to solve that. And we had 4 or 5 options from the paper of Govindarajan from 1991 to some recent papers, which we were considering. Luckily, the first one which we tried after our mathematical hunch, that worked out and we got close to 23% of the performance improvement. So that involved a mathematical hunch while choosing 4 or 5 possible solutions. I am seeing typically in the industry with the decline of these mathematical foundations, if there are 10 options, they are saying, oh, let's try them. And after the results, we'll choose which one. So this one hunch, which first one worked correct, it took 6 months for us to implement. So if we start trying 10 things before implementing and not having a mathematical judgment, which one may work. So there are thousands of things happening in academia, thousands of things happening in, community, open source community. We are not going to launch good products in good time. So it is extremely important. So I seek help from, because our compiler example, I will not say that we are perfect, but has worked. We are getting reasonable amount of talent now. Like, for example, I really felt happy with when Saurabh sent out an email in IIT Delhi to cs.all. I was copied a few years back. If you want to work in compilers, Qualcomm is right place. So it's not that I'm selling Qualcomm out there, because we did these presentations. That's why Saurabh felt that we are a team and we are getting people because of that. And there are more people graduating in compilers than 7 years back, as far as my observation is. So this works, may not be in a miraculous numbers like the way you will get AI ML candidates or CV candidates, but from 0 to a better number. So I request everyone from industry out here and academia, if you have any suggestions, we are more than open. And in academia, I'll request you work with your other industry contacts if they can prepare a similar thing for other subjects. That will be great. Any questions? Questions? Yeah. Yes. Pati.
So Qualcomm now has a formal verification team, right? I mean,
Oh, we have, earlier my presentation was I was planning to run through, so our hardware teams uses more than what we saw in software we do. So hardware team, the contact point is Shravana in
Shravana.
Bangalore.
Yeah.
Shubhajit interacted with them quite in detail. In software, our compiler team uses program analysis. We did a small part of LLVM essay. There's a larger program analysis team, but they are mostly in US and Europe who are using formal methods. So these are the three major teams which we are using, which I know of. There might be more.
So the team here is mostly doing hardware verification,
In the Bangalore, yes.
and the software verification is somewhere else, is it?
So for formal verification, we are mostly using in program analysis, static analysis.
Okay.
As far as I know, Qualcomm is a large company. I may not be knowing about a lot of teams, but yes, because we have like other companies, we have like TCS Research. We also have our Qualcomm. We go by a single name, but we have a corp R&D division. They do much more than what we do, so they might be doing more. I may not be aware of, but this is what I am aware of.
Yeah. So I think just like you said that Saurabh announced.
Yeah.
And you maybe gave a presentation there. So if Shravana can come or whoever can come and
Sure.
actually give presentations to students around, it will.
Yes. So
Because what you mentioned is very true. I mean, everybody wants to do AI ML and they don't even want to come like 100 feet.
Oh no, the fun part, they don't want to, they even don't want to do AI ML. Our AI ML team, we had people whom we were optimizing architecture for AI ML. They said, no, this is not AI ML. I want to call that library. so for AI ML also, for faster execution on DSP, we are optimizing the architecture. That is not AI ML. So mathematical foundation of AI ML is not AI ML. Well, jokes about it.
Yeah, I think it'll be interesting. Clark will give a talk on when AR met AI to the automated reasoning.
Sure. And one thought that comes to mind, very quick thought that comes to mind to kind of make proofs a bit more kind of engaging is to kind of model them as you would do programming. If you use automatic theorem provers, they have this programming component about them, but they are also about doing proofs. So I was just wondering, on the top of my head, whether if we introduce students to these kind of software-based, but something which can code up. Okay, so kids who are coming in, the fresh out of school kids who are coming in Qualcomm right now, especially my team around. So it's not my presentation. I reuse the Leslie Lampert's famous presentation of how to write proofs or how to present proofs. So we run it for them. I think he's even developed a software, right? For Leslie Lampert has developed software for doing. But we are using his presentation. That video, we memorize that video and we just replicate it. So we do like we bring in Leslie Lampert's soul inside us and then we deliver it. Thank you. Okay, I think this is a very nice talk. Thank you, Sushil. Of course, we'll have more discussions during in the break, but I will stay back for probably lunch and so that we discuss. I want to meet this community. We are getting extinct. No, not in academia or some people in industry, but at least in students they are getting extinct. Extinct. So we need to survive. Okay. Thanks again, Sushil. Yeah, our next speaker is Arijit Shaw, who's doing his PhD at CMI, and also working with Kuldeep. And he's going to talk to us about an approximate Skolem function counter. Presume this is, yeah. Am I audible? No. Hello. Yeah. Thank you.
Yeah. So thank you for the introduction. So I am Arjit Sahu. I'm a PhD student at Chennai Mathematical Institute, jointly with IEI TCG Crest, that's in Kolkata. And today I'll be talking about our work on building an approximate Skolem function counter. And this is a joint work with Brendan Juba and my advisor Kuldeep Mill. So let's get started. So I'll start with a different problem that which is much well known, and that is the problem of functional synthesis. So in case of synthesis, you are given a set of specification that spans over a set of input variables, we'll call it X, and a set of output variables Y. And those specification tells you the relation between those input and output. So the problem of Boolean function synthesis is that you are given the specification as a Boolean formula over this input and output variables, and your task is to synthesize a function that will satisfy those specifications. Now, this synthesis problem gives you generally a circuit which represents this function. Now, let me give you an example to make things more clear. So let's say the function says the specification says that the function should encode the factorization of a 4-bit number. So you can encode this specification like this, that x equal to y1 and y2, and y1 greater than equal to y2, y2 greater than 1. And you can design many different functions that satisfies this specification. For example, you can come up with a function that if you give that function 12 as input, that will factorize it as 4 into 3. I can come up with another function that will factorize 12 as 6 into 2. So there can be multiple functions satisfying the same specification. The problem we are interested today is, given a specification, we need to count how many such different functions exist. So what are different functions? So we call two functions as different if they are semantically different. So two different functions should differ on outputting on at least one input. So let me give you an example. Like, let's say you have a specification over just one input bit and one output bit, and the specification says that the output should be greater than equal to the input. Then you can just design this function as fx equal to x. That will satisfy this specification. I can come up with another function that fx equal to not of x. So that is, the circuit will look different, the function will look different, but the input-output behavior is exactly same. So we'll not differentiate between these two functions, as the output behavior is exactly same. Now, if you come up with a function that is, let's say, that outputs 1 on all the inputs, that is a different function, because this has a output behavior different than the other ones. Okay, so let me tell you, so I think this function, same function and different functions definition is clear. Let me give you so now we'll come to this Skolem function part. So this idea of Skolem functions came from Thoralf Skolem like 100 years back, and he came up when trying to solve these first order formulas. And in case of first order formulas, if you have some existential variables, and if you want to get rid of these existential variables, then you can replace these existential variables with some functions. For example, here you have this existential variables y, and you are replacing those y with function of gx. So the task of synthesizing is like exactly this problem, that you should come up with this implementation of function gx such that it satisfies this specification over f of xy. Now, this difficulty of counting Skolem function is probably hard. We do not know the exact complexity of this problem, but like traditional model counting techniques are not supposed to work in this case, because these model counting techniques either makes a succinct representation of the whole solution space, or at least enumerate a few models. We do not know how can we do this in case of functions. Also, there is another difficulty, that this number of functions can grow as large as 2 to the power y into 2 to the power x. So there is a 2 to the power x, and in practical cases, this number of x variables can grow very large. So this number is the number of functions itself is very large. So as this number is very large, and like representing these numbers, such a big number is very difficult, we are interested in approximating the logarithm of the count. So we are not counting the number or approximating the exact count, or approximating the logarithm of the count today. And today we will rely on these model counters and samplers very much. So there has been a significant development in these fields last 20 years. We'll use all those developments in our work today. So let me give you an intuition on how function count should work. Let's say we'll deviate a little bit from this Boolean function domain for a moment. So let's say we have a domain of size 2 and a range of size 3, and we want to calculate the number of functions that can be mapped from this domain to this range. Then we can list down all those functions like this. And as you can see that this number of functions here is simply like range to the power domain. Now, if you have some specification and the specification makes some constraint on this function, let's say 2 can map to only 7 and 6, then this easy formula will not work. And in this case, we have to look at every element in the domain. We have to count how many elements that element is mapping to, and we have to multiply all those numbers to get the number of functions, right? So, and if you want to calculate the logarithm of this number, that is essentially the summation over log of range for each of these numbers. So then essentially this counting the number of function is effectively calculating this number. So there is just one problem, that what happens if there is some element in the domain for which there is no element in the range. If your specification says something like this, so do you say that there is no Schollem function exists for this specification? So that is not the case. That depends on how we define the problem. In our case, and like also in synthesis, we generally say that if that is the case, there is no element that maps from this element, then like we can output anything for that. So to make these two cases separate, we will divide our input space into two parts. Let's call the sets S0 and S1. S0 contains all those elements from domain for which there is no element in the range, and S1 are all the remaining elements. Now, as we are calculating this number, this summation of log of range, it is not a very difficult problem to do. We have to pick all elements from the set S1. We have to calculate the range for the element, and we have to keep on summing up this log. So the task now is calculating this range. And how can we do it? We can use these model counters to count them. So we will pick this specification formula f of xy. We fix x to sigma, and we will put this formula to a model counter. The only problem is we have to repeat this procedure for all the elements in S1. And S1 is exponential in size of the input variables. So like we have to essentially call exponential number of model counters. So once we are done with calculating all the elements, we will get the sum. We have to make some modification, like add some elements to accommodate that set S0. And once we will get the number, but we will need to call this exponential number of times. And SAT is hard, model counting is even harder. So exponential number of calling this problem is not that a good thing. So can we do something better? So as you can see that we are calculating this number. Can we approximate this number with some theoretical guarantees? We can look at it into some other way. We can write the same function as this number. And when we are doing this sum, this is effectively estimating the value of log of range of sigma over all the elements in sigma. So we are calculating this estimate here. Now, for estimation, we have different of these techniques that works well, and Monte Carlo estimation is a good technique for that. In that case, we do not look at all the elements from S1. we sample some of them and then make an estimation from those samples. So the problem of Monte Carlo estimation is we have a set of random variables, and if those random variables lie between 0 and 1, then we have algorithms that run for order of t by mu many by taking t by mu many samples, and gives you an estimate of mu within some additive bound of epsilon with high probability of 1 minus delta. Now this t is a function of epsilon and delta, and mu is the mean. Now we are calculating this. Our range of sigma lies between 1 to 2 to the power y. So the log of range of sigma lies between 0 to y. And if we take this parameter as log of range of sigma by y, that lies between 0 and 1. If we take that as our random variable, then we can use this Monte Carlo estimation technique for that. But what is that? How many samples we need? As we showed you, like the number of samples that we need is t by mu, but we do not know the mu. Mu is the parameter that we are estimating. And as you can see, this log of range of sigma by y, that can go as low as 0. So this mu might go to 0. So we do not know what is the lower bound on that. To get a lower bound on this, we need to do some other trick, that we will separating this set of whole input space into 2. Now we'll divide it into 3. Like we have this set of S0 where range of sigma has no element. We will make this S1 as those elements in sigma for which there is only one element. We will have the range set S2 for which there is more than one elements in range. Now, how can we pick things from S2, or how can we separate? We have to create another formula G in this way from this specification formula. Now, if we pick satisfying assignment from G, then those X will refer to elements in S2. Now we have log of range of sigma by y as a value of 1 by y. So it will not go till 0. It will, the lower bound on the mu will be lower bound of this, and we will require a number of samples of order of this. And now we will require only linear number of linear or many samples to estimate this value. So instead of taking exponential many model counts, we need only linearly many model counts to get the estimate of this number. So what is this algorithm that gives you order of t by mu many samples? So this algorithm the credit for this algorithm goes to Dagum et al. Back in 1995. The algorithm is very simple. It is like you set up a threshold from epsilon of your desired epsilon and delta. You generate a random variable Zi, sum up the Zi, and you repeat until that sum reaches this threshold. And once you reach the threshold, you divide this threshold by number of iterations that it take to reach this threshold, and that will give you the estimation of this random variable. Now this stopping rule theorem says that the estimation that you get from this algorithm comes up with this additive bound, and that is with high probability of 1 minus delta. We will use this algorithm to design our function counter. We call it Sat+Smt. And this will work in this way, that we will sample a sigma from this set S2. We will calculate the range for that sigma. Similarly, we will use this model counter to count this sigma, and we will keep on doing the sum to keep up doing this sum until we reach the threshold. The threshold is similar as this stopping rule algorithm. And once we are done, we will get this number of Sat+Smt functions. So yeah, so instead of getting this exponential number of model counter calls, in this case we will need linear number of model counter calls. and we will get the estimation of number of Skolem functions within this additive bound. So we showed in the paper that we will not exact sampler. We can use with this almost uniform samplers. Instead of exact model counters, we can use approximate model counters. So we need to do a little bit more iterations than earlier to accommodate all the errors that are being introduced by the samplers and counters. But in practice, they are performing really well than exact and approximate model counters. Well, so this is our algorithm. So is this a theoretical algorithm only? No, we implemented it. And let's check the efficiency of the thing. First, we will check how many model counters call we require. So we took a set of 609 benchmarks that come from this synthesis benchmarks, and it is used in synthesis. And number of counter calls needed in the instances for the baseline. So the baseline is, we do not have, so this is our first algorithm in this problem. So we do not have a baseline for checking the performance of our algorithm to check against. So we use that naive algorithm as our baseline that takes this exponential number of model counter calls. And so this baseline algorithm takes as many as like 10 to the power 224 model counter calls. And when we look at our implementation, it takes around like 100 to 10,000 number of model counter calls. So that's an improvement. And when we checked the time and we gave 10 hours to the algorithms on these 609 benchmarks, and we found that like this baseline can solve only 8 benchmarks out of all these 609. And when we tried our algorithm Skolem-FC, it can solve probably 379 instances. So that's a significant improvement. And just to put in context, like Skolem-FC can solve 379 instances in 10 hours. So the state-of-the-art synthesis engine that can solve 509 instances in actually 2 hours. But we didn't check it for how many instances that is solved in 10 hours, but like the numbers shouldn't be very different. So like solving a quantitative problem instead of a synthesis problem in similar range shows that our algorithm is doing at good as it. So that's the performance. And when you look at the correctness of the count that are given by our algorithm, so we looked at the exact count. So we do not have many instances. So we generated a very easy instances to check the correctness. So we generated 160 very easy instances that for which we can get the exact count. And we plotted like the upper bound and lower bound from that exact count. And when we looked at the performance, the count returned by Skolem-FC, that lies well between these two bounds. So that shows that in practice, this number is lies well between both the bounds. So I should have shown this slide in the beginning, but why are we interested in counting functions? So does it have really any practical implications? So first answer will be like when we can solve easier queries, we look at richer queries. For example, like when we can solve SAT easily, we went towards model counting. So from yes, no answer, we went to like number of solutions. So we can solve other questions now, like we have good QBF solvers. We are very good at SMT counting, SMT solving now. Now, when we have solvers for this, we are answering more expressive theories. So what are the quantitative questions for them? For example, for QBF, where we do not have this exact notion of some model, what can be the quantitative question? And one of the answer might be like number of functions in that case. When we look at SMT and we reach to these uninterpreted functions, we might want to count the number of these uninterpreted functions. So in these cases, like this column count is nowhere near the first domain of underinterpreted functions, but we can look at as a first step towards counting those functions. And like these numbers might be important in some cases. For example, in security domain, like people often want to obfuscate some of their implementation by replacing the existing implementation with another implementation that satisfies the same specification. And when we have the numbers, we can get an estimate like how well we can generate some other implementation of the same specification. So these numbers might be important, but as this is a first work in this, like people might, like you and some other people might be interested in reducing their problem to this counting of functions problem. So that's all. This is like the first work, and we have designed a algorithm for counting higher dimensional object. And definitely we are looking for applications for counting this number of functions. So that's all. Thank you. Our tool is available online. You can check it out.
Thanks for the very nice talk, Arjit. Questions?
Yeah.
Yes. No. Good exercise.
Okay, sorry. Yeah, well, very nice, actually. I'm a bit surprised. So if you go back to the slides where you're doing better than Mantan, which I think is, rather funny, I would say. So you can count the functions faster than solving. That's like saying, I'm better at solving than I am at model counting, right?
Not really.
It's not really, but it's also kind of it's kind of strange. Can you explain what's happening here?
So like, let's say for like the problem of propositional model counting is definitely harder than SAT solving, right? Because if you know the count, you definitely know the answer, yes, no answer for SAT solving. But that is not the case here. We are not even synthesizing one function. We are just looking at the input-output behavior, and from that you can say that like what are the number of functions. And as we are defining the problem in the beginning, that like there can be multiple same implementation with same input-output behavior, that f of x equal to x and f of x equal to not of x. Those are different looking functions, but we are counting them as one. So like this synthesis and this count are not exactly related.
I understand what you're saying, and I think we can take this offline, but just one feedback to that is that if you weren't counting approximately, then most normal model counters would actually compile this thing into so the first thing that it reaches would be one solution, and that you could just terminate. So the approximate part, I think, really plays an important role here, because without approximation, the current set of algorithms that we know compile this thing. So it would not only literally would enumerate every single one of them individually. So obviously taking one would be trivially simple and should be significantly simpler. So it really either has to do something with approximate counting, or the current synthesis systems are very poor compared to
that is not the case. Like the first one is.
Yeah, the approximate thing is what you're saying.
Yes.
That's what really makes the difference.
Yeah, that is also another thing that like we didn't run Manthan for 10 hours. These numbers for Manthan is from 2 hours. But as Priyanka said that like this Manthan, if you give Manthan more than 2 hours, it will not solve many more instances. But yeah, this is not a very good comparison to do.
Okay. I think if it's a short question, that's okay. May not be short.
Okay, so I'll just leave you the question. You don't have to answer it. So maybe I don't understand this problem very well. So, but what I understand is, so there are two parts of it. One is that your inputs are controlling some output variables, and it is not controlling outside variables in the output domain, right? So I can partition the outputs into sets which are controlled by the inputs, and a set of variables which are not controlled by the inputs.
No.
Which you said, you said, for whatever is don't care, I can assign it to anything, right?
Yes.
So now what the ones that are don't cares, I know how many solutions are there, because 2 to power how many are remaining. So that is the count. right? And for the ones which are controlled, I have to sort of count how many satisfying assignments I have with the input and the output relation.
Yes.
So I think I'm missing something, but is it more than this? So maybe I'm not getting it completely, but maybe I'll take it offline. So it's a longer question.
Sure. I'm happy to.
Yeah, I think it's a very interesting question. Yeah, we'll just in the interest of time, lots of good discussions. So thanks for the talk that you have spurred any questions. So yeah, I think we'll thank Rijit for this nice talk. And our next speaker is Priyanka, who is faculty at SISPA. And she's going to talk to us about synthesis with explicit dependencies. While she's setting up, I'll a little historical anecdote about Skolem. So it turns out that Skolem introduced the idea of Skolem functions to set right a wrong proof or an incomplete proof by Lowenheim back in 1915 when he gave the first proof of the Lowenheim-Skolem theorem. And the proof was it used Koenig's lemma, which is not yet proven then. So to fix that was Skolem introduced the idea of Skolem functions and then, of course, gave a self-contained proof and then generalized it to the most general version of Lowenheim-Skolem. So we should thank Lowenheim for making the error so that Skolem could fix it. As they say in the Surf Excel ad, daag achhe hain. Yeah, so Priyanka.
Hi, thanks for the kind introduction. Hello, everyone. I'm Priyanka Golia. I'm a faculty at SISMA, Helmet Center for Information Security. And today I'm going to talk about synthesis with explicit dependency. Arijit here set up a nice background for the synthesis and to count the number of functions with respect to that. So we are going to take a step backward and see how we are going to synthesize these functions. This is a joint work with Shubhajit Roy and Kuldeep Singh Meer. And I'm going to take this opportunity first to say that if you are a student and you are looking for internships, PhD and postdocs, let's chat. I'm going to be here for the entire conference. So let's start. Synthesis. What is a synthesis? In a simpler word, we can say that the user states the problem and computer solves it, right? So suppose we are dealing with set of inputs x, x1 to xn, a set of outputs y, y1 to ym. And we have an underlying specification, which we are representing here as phi, over this input x and output y. What we want to do? We want to fill this black box, the black box that takes x as an input and somehow computes output y, such that when you put together this x and y back into the specification, they satisfy the specification. This black box can be filled with any program, any circuits, or more generally, functions. We can synthesize functions corresponding to each output, each yi in terms of input, such that they satisfy the specification. But this is just a synthesis. Today, we are going to talk about synthesis with explicit dependencies. What are they? Let us take an example to understand. Suppose we have given a specification and an incomplete implementation of that specification. So our task here is to complete the implementation such that it becomes functionally equivalent to the specification. Look at this picture that we have here. You notice that this particular part is the specification, and this dotted thing is the incomplete implementation. Why I am calling it incomplete? Because these two boxes, black box 1 and black box 2, we don't know what is there. It's just the black box for us. We want to complete that implementation such that it becomes functionally equivalent to the specification that is provided to us. You notice for this implementation, we have two inputs, x1 and x2. But if you just notice for black box 1, it just takes x1 as an input. It has no relation with the x2, right? And if you notice at the black box 2, it just takes x2 as an input. It has no relation with x1. So these are the explicit dependencies I'm talking about. So what we have to do? Okay, so we have inputs x1 and x2, outputs y1 and y2. And what we want to do, we want to synthesize function circuits corresponding to y1 and y2 such that they satisfy the specification. That is the task. With the explicit dependencies given to us. And this particular problem is a well-known problem of partial equivalence checking. And this particular problem is also known as Henkin synthesis in the literature. So let us try to formalize the problem statement here at this moment. Again, Inputs x, x1 to xn, outputs y, y1 to yn. Specification over this input x and y, which we are representing here as phi. For each output yi, we have explicit dependencies, which we are representing here as hi, which we call Hankin dependencies. This hi are the subset of the input set that we are provided to. So this is the dependency quantified Boolean formula that is provided to us. And our task, our objective is to synthesize functions corresponding to each yi in terms of only its Hankin dependencies, such that if you replace yi by those synthesized function in the specification becomes a tautology. That is the task that is provided. That is the task that we have to do. These functions are called Hankin functions in the literature, and we are interested in synthesizing Hankin functions efficiently. Okay. This particular problem of Hankin synthesis has various applications, from quantifier elimination to circuit repair to cryptanalysis, reactive synthesis, program synthesis, and many, many more. Coming back to the example that we started with, now we can say that the Hankin dependency corresponding to y1 is x1. The Hankin dependency corresponding to y2 is x2. And the specification formulation, we can write that for all x1 and x2, there exists y1 depending only on x1. There exists y2 depending only on x2, such that this specific incomplete implementation becomes functionally equivalent to the specification that is provided to us, that we encoded. So now, if we can synthesize Hankin functions corresponding to y1 and y2, that will be the black box 1 and black box 2 for us, right? So how does this Hankin function look like? Let's take a toy example here. So we are dealing with two inputs, x1, x2, one output y1, and we say that the y1 has an Hankin dependency x1. It is only allowed to depend on x1. And the specification that we are dealing with is the disjunction of all this x1, x2, and y1. We want to synthesize Hankin functions corresponding to y1. What can be then Hankin function? One Hankin function could be negation of x1, right? It takes x1 and negate it. That will be the. Why we are calling negation of x1 as a Hankin function? Because in the specification, if we replace y1 by the negation of x1, it becomes a tautology. For all possible valuations of x1 and x2, the specification in which we have replaced y1 by the corresponding function becomes true. So we can say that the negation of x1 is one possible Hankin function. But as in the previous talk by Arijit, we noticed that these functions are not unique, right? For example, in this toy example, we can see that not just the negation of x1, a constant function 1 would also suffice. So we are interested in synthesizing Hankin function. And for that, we propose Manthan. Again, sounds familiar. Arijit compared with the Manthan, right? So Manthan take advantage of advancement in constraint sampling, machine learning, and formal methods together to synthesize Hankin functions efficiently. The framework of Manthan takes this specification as an input. It first relies on the constraint sampler to generate some data. Once it has the data, as we all know, once we have the data, we are going to use machine learning algorithm to come up with the candidate functions. Once we have the candidate functions, we are going to rely on formal methods to formally verify whether these candidate functions are indeed the Hankin function that we wanted. If not, these candidates will undergo a repair iteration. So this is the framework of Manthan. Data generation, learning candidates, and then verifying and repairing them. I'm going to give you a quick overview of all of these components. First is data generation. For that, Manthan stands on the shoulders of constraint sampler. What is a constraint sampler? Constraint sampler takes the specification as an input and generates the satisfying assignment of the specification given as per the distribution. For example, if we are dealing with a uniform sampler, it will take the specification as an input and generate the satisfying assignment uniformly at random from the solution space. If you look at this big circle, it is the all possible assignments to the variables of a formula. And the small gray circles are the truth assignment, the assignment of which the variable becomes true. The formula becomes true. And a constraint sampler is going to generate these satisfying assignment as per the distribution that is given to us. For example, if this is the specification that we have, each row of this data will be a satisfying assignment for us. Once we have the data, the next step for Manthan is to view it, to learn the candidate functions. And for that, Manthan view it as binary classification problem. For example, if we want to learn candidate functions corresponding to the Y2, then the explicit dependencies for the Y2 was suppose X1 and X3, then the valuations of X1 and X3 in the data will act as our features. And the valuations of Y2 in the data will act as our label. And with these features and label, we will learn a decision tree to represent Y2 in terms of X1 and X3. Similarly, if we want to learn the candidate function corresponding to Y1, then the valuations of Hankin dependencies of Y1, which is X1 and X2, will act as our features. The valuations of Y1 will act as our label, and we will learn candidate functions corresponding to Y1 in terms of X1 and X2. So, how these candidate functions are going to look like. Suppose this is the decision tree that we got by learning in the learning phase, then it is corresponding to the Y1, which because we are using only X1 and X2 in the decision node, which is the Hankin dependencies corresponding to Y1. Then the corresponding function will be the disjunction of all the paths that leads to the leaf node 1. Suppose this is the first path in which we have X1 as 0, X2 as 0, then the leaf node is 1, which is path P1. The second path when X1 is 1 and X2 is 0, then the leaf node is 1. So disjunction of all the paths that leads to the leaf node 1 will be our candidate functions that to deal with. So Manthan generated the data, come up with a candidate function. Now we have to verify those candidates, certify those candidates that these are indeed the Hankin function that we wanted, or otherwise they have to go into a repair iteration. For that, we rely on formal methods. So we certify, we try to use, we verify, and then we say that, okay, if they passes the certification check, then we say that, okay, we have found our Hankin function and we can return those, and we are done. Otherwise, we have a counterexample. That counterexample will say that, oh, for this particular valuations of the input, whatever you have synthesized does not work. They do not satisfy the specification. Then we try to extract out the reason. Why? What is the reason behind that for this particular input, the candidates that we have synthesized so far do not satisfy the specification? We extract out that reason. We use that reason to repair the candidates. And this loop continues until unless we say that, oh, we have verified it. We have found our Hankin function. And for that, again, we rely on progress in set solving. The verification check is nothing but a set solver check. We check whether when we substitute the Hankin function in the specification, it becomes tautology or not. If not, we have a counterexample, and then we try to extract out why this counterexample exists using the unset core identification. And we use that to repair the candidates. I'm not going to go into the details. I'm around to discuss more about it. So this is the framework that we have. Data generation using constraint sampler, learning candidate functions by viewing it as a binary classification problem and learning decision trees, and then verifying and repairing them using formal methods. This is the Manthan for us. And to check where does we stand with respect to the experimental results, we compared Manthan with the state-of-the-art Hankin synthesizer, HQS and Pedant. HQS is an expansion-based DQBF solvers or synthesizer, and the Pedant is interpolation-based Hankin synthesizer. We experimented over 550 benchmarks arising from various sources, and we gave the timeout of 900 seconds. So here are the results. We compared Manthan against the virtual-based solvers of HQS and Pedant. What do we mean by virtual-based solver? Virtual-based solver is at least as powerful as the solvers that are there in the portfolio. For example, we say with respect to HQS and Pedant, we say that the VBS solved an instance if at least by the HQS and Pedant it was solved, and the time taken will be the minimum of them. So, and as the plot that you are seeing here is a cactus plot, in which on y-axis we have runtime, On the x-axis, we have number of benchmarks, and a point xy represent that a synthesizer took less than or equal to y much time to synthesize functions for each of these x many instances. So towards the right is the better. And we can see that when we include Manthan in the virtual base solver, we see an increment of 26 instances. So Manthan was able to synthesize function for 26 instances that was beyond the reach of the state-of-the-art solvers before Manthan. So that's the increment that we see. And before concluding, let's get back to the thing that are you looking for internships, PhD, and postdocs? And for that, I would say CISPA is a place. CISPA Holmer Center for Information Security. It is a German nation science institute. Just in the Germany, there are two big research society. One is Max Planck and another is Helmers Association. And CISPA is a part of Helmers Association. And it is always looking for interns, PhD, and postdocs. There is no particular deadline for PhD and postdoc applications. You can apply throughout the year. For internship, there will be any specific calls. And CISPA is particularly interested in hiring South Asian students. And there is, in fact, right now, there is a call for South Asian internships, which you can apply. So why CISPA? Because you are here right now attending the Sat+Smt workshop. So I'm assuming that you are interested in formal methods. So I'm just going to list out the people who works in formal methods and software engineering at CISPA. So for example, if you want to work on the automated program analysis, testing, and debugging, then Andreas Deller is the person, right? If you are interested in reactive synthesis, hyperproperties, model checking, quantitative verification, and so on, then Bernd and Rainer is the person to contact with. If you are interested in formal verification, parameterized systems, settings, and so more, then Sven is the person to do it. And if you are interested in AI plus formal method fusion, then let's chat. So you should apply to CISPA. Do consider visiting the website of CISPA. On that note, I would like to conclude. We talked about Manthan for synthesis with explicit dependencies. And we see the magic of constraint sampler, decision tree classifier, and formal methods all together for the Henkin synthesis, and with which we can solve additional 26 benchmarks. The tool is available open source. Please give it a try. Thank you.
Thanks for the very nice talk, Priyanka. Questions?
So you also talked about this this block diagram that you had. There is a repair block. So could you elaborate a bit on this? If the repair block is also related to this learning block, I mean, does it get any?
Once we have the candidate function that is fixed, we do not go back to learning phase. So it's a sequential thing that we do. We first generate the data, then learn, and then we go into the repair. We do not go back to the learning phase.
So
but the repair is the candidates that we have generated using the learning part. We are trying to repair those.
So when you repair, then you change the candidate function possibly, right?
We are repairing them. Yes, yeah, we change them. We introduce changes in order to make sure that these are the Henkin functions that we wanted. Like we make it towards them to the Henkin functions in some sense.
So yeah, I mean, I was trying to understand like why the learning cannot be instrumental in the repair part, or
it can be, but for the set of benchmarks that we are dealing with, we found that this is the perfect one. But it might be happen that you want to generate data again because the repair is taking much of a time, and then use that data and run it again and so on. That is possibilities, but this is one of the framework that works well for our benchmarks, in which we say that, okay, we have learned and we will just stick to it. We'll not go back into the again.
Okay. And another second question that I have is like, if you use these dependencies, does the problem become harder?
Yes, yeah. It's
I think in general, like DQBF is possibly has some much higher complexity, but otherwise also when you try to synthesize, you see that.
Yeah, it inherits the hardness actually.
And what is the intuition? Because it seems to me like maybe you have to search in a more constrained space, so the search space should be smaller because you have this specific dependencies. So somehow to me it looks a bit counterintuitive. So
just one small example, just to like a column function in which we don't have this explicit dependencies and a y is allowed to use all the inputs. A column function may not necessarily be an Henkin function, right? But the vice versa is always true.
Okay, yeah.
Yeah, so then basically from that you can see that for this Hankin dependencies are actually the hardness is inherited in the synthesis as well.
Okay.
Yeah.
So are the synthesized Hankin functions optimal in some sense? Basically saying that, so no such guarantees you give?
We just say that it is an Hankin function. We don't have any guarantees with respect to the optimized function. There might exist some smaller function in terms of sizes or anything. We don't say any, like no optimization guarantee.
Do you see any opportunities where SAT can be used to optimize the given circuit in some way?
Of course, we are looking into it, but at this moment, I don't have any idea about it. So yeah.
So I have a question regarding the time, in the three phases, where is it the most amount of time going? Is it in the learning or in the repair?
In the learning, I would say, because if you notice that for each of these Y variables, we are learning decision trees separately. So if we are working with tens of thousands of variables, we are calling the decision tree based algorithm tens and thousands of times. So learning is currently the black box. Yeah. Yeah.
And another question that I have is, there seems to be this spectrum where you can sort of generate more data and learn for longer, or you can say learn quicker and then spend more time repairing.
All these is possible.
But so on this spectrum, where do you think, according to your experience at least, where is it that like it was better for?
So what we did is we fixed the number of samples that we are going to generate. And after that, the learning and repair will come into the picture. So once we fix the data that we have learning is going to be like the time is like as you increase the data, then the learning time is going to increase. Otherwise, it's going to be the same. So we fix the number of data that we are going to generate, and then we follow the rest of the timeline. That's what we are doing. But of course, as you increase more data, then it might be possible that we are learning more good candidate function that leads to the less number of repair. It might be possible. We cannot, before experimenting, we cannot comment whether this is true or not.
Okay, thanks.
Hello. Yeah. So because you are only looking at the sample and not the entire solution space, and your repair cycle does not go back, call the sampler again. In this process, let's say that there is no solution. Solution does not exist. Can you, with this process, definitively make the statement that the solution does not exist?
So if the DQBF formula, underlying DQBF formula we are working with, if it is true, that means then definitely this loop is going to terminate. That means there exists an Hankin function. If we are dealing with the underlying DQBF which is false, then this loop might not terminate. But so we are assuming that in order to synthesize, we say that the DQBF formula is true, and then we want to synthesize functions corresponding to it. That's the.
So yeah, like from that point of view, I think even Shivashish made that remark. Maybe it might help to kind of go back to the sampler.
But when DQBF is false, we don't know what do we mean by Hankin functions. Hankin function exists when the DQBF is true, and that's why we say that, we can, what is the functions corresponding to that?
No, that's true. I'm just saying that basically to be able to reach a point where, let's say that you have unbounded time, to be able to reach a point where you can make a definitive statement that no solution exists.
Yeah, we can look into it. I am not sure.
Other questions? One quick question. So the repair that is there, how do you do the repair when you find something? I mean, what is the way in which you go about doing the repair? I mean, I hope I'm not missed something.
No, so we actually use this unset core based identification. So we come up with one more formula saying that why this particular counter example exists, why for this particular valuations, whatever we have synthesized do not satisfy the specification. So then it will be a set of constraints which will be violated. We try to extract that out. And then we say that if this is the case, if this is the input, then output should be toggled or something like that, because it's a binary.
So that unsat code is kind of muted. Kind of you change the unsat code.
We extract that unsat code and try to reason about it, like why this exists, and then use that to repair it.
When you use it, you change it in such a way that it you kind of
toggle it. Yeah. For this particular input, the output is toggled. So that is why it's a binary case.
Okay.
We can just toggle and then.
Okay, sure. Yeah. Okay. Is this loop why this is called Manthan? Is this the churning that's happening?
That Kuldeep is there. I guess that's a question for him.
Right? This is the churning that has yielded all this Amrit. This is the one, right? Huh? All the three. There are three parties that are kind of.
So right now I'm giving a talk in front of formal method. So we can say the God is formal method and the devil part is AI, and then we are trying to do Samundra Manthan sort of a thing. Yeah.
Wonderful.
So-
Wonderful. Any further questions? On a historical note, why are Henkin functions called I mean, how come the term Henkin function? Because there's this notion of Henkin models and adding constants and so on, kind of this proof of compactness using Henkin models. Is there a connection between this and Henkin functions? I suppose it's the same Henkin. Henkin quantifiers.
The explicit dependence.
I see. I was not aware of. I have no Lindstrom quantifiers. Is a Henkin quantifier. I see. This is interesting. There are Lindstrom quantifiers. Those are generalized quantifiers, but Henkin quantifiers are. This is a known. I see. This is Henkin. I see. Wonderful. Okay, I think we've had a nice session. Thanks, Priyanka, for this very nice talk, and and thanks to all the speakers for all their talks. Had a nice and engaging session. All the questions that we have asked, and a lot more questions during the break. I think we should go for lunch. Thanks for this time that you maintained. You have gained some time. So so we should yeah. So I think we should go for lunch. And 2 o'clock. Kuldeep's talk. 2 o'clock. Looking forward.
I don't have any problem stacking this particular part, but it should not give you that policy. Because when you
नहीं वो जो स्विच प्रोजेक्ट वाला
डुप्लीकेट ना,
हाँ
पर वो अलग है क्या?
नहीं वो यही वाला है, यही है वो चल रहा है।
एक बार देखिए।
वो जस्ट वो प्रोजेक्ट स्क्रीन वो क्या ये वाला ऑप्शन था ना।
हाँ हाँ, नहीं ये अलग हो गया। नहीं एक सेकंड,
ये नहीं
एक सेकंड।
पीसी स्क्रीन ओनली नहीं, डुप्लीकेट एक्सटेंड ये नहीं हो रहा है।
नहीं आ रहा।
ये प्रोजेक्ट नहीं हो रहा। इसी के प्रोजेक्ट करने की जरूरत नहीं है यहाँ।
अच्छा ठीक है, यहाँ पे देख लेते हैं। ओके, बट ये क्यों ऐसा आ रहा है? जस्ट मिनट में।
नहीं वो आप आई थिंक वन ऑफ दोस ऑप्शंस
नहीं मतलब ये वो हैंग हो गया क्या? Okay, let me just restart it.
Yeah, I think it's working now. We'll just try and do that one.
I need to just start here. Just I will take 2 minutes. वो भी एक रिक्वायरमेंट है उसका।
That is not for every atom in predicate, you do this thing. What does it mean? For every atom,
इसको निकाल देते हैं, नहीं लगा देते हैं, ठीक है। अच्छा हम लोग लैपटॉप में ही देख लेते हैं, इज इट ओके? ठीक है, Okay, first of all, जो मेरा no, but let me, because what had happened ना, मैं MCDC ले लिया ना, वो गलती हो गया actually. But what I want to show. Okay, first let us compile this one. Okay. इसका हम लोग output store कर लेंगे. Just a minute. CBMC, yeah, I got it. मैं बताता हूँ.
कंपनी का पॉलिसी है कि लाइक होस्ट कंपनी अलाउ कर रहा है या गेस्ट कंपनी अलाउ कर रहा है.
ठीक है.
होता नहीं है. Google have that series of talks where there are like people from other.
Okay.
Like,
बस 2 मिनट.
like for example, very dedicated. There are things where which we have made it public. I'm allowed to do talk anyway. Could be private company. That is right. Which
Okay. Can we see here?
After that, I can talk about it.
Okay, Divish, you can also come. See, that program right now. Okay, this is the program, the simplified one, because already है. इसलिए मैं उसको ना condition option लेके no MCDC, ठीक है? इसको लेके मैं संगू 4.txt में मैं save कर रहा हूँ. Okay, that I will open it. संगू 4. This is the output I got. Okay, now मेरा जो point था, like इसको हम लोग comment कर देते हैं, right? And I just bring it as a predicate. ठीक है? Like this. Okay. And this is artificial. I want to make it dead. Okay, first of all. And I want to run it. And I'm saving in Sangu 3.txt. ठीक है? Everything is same now. Right? Just मैंने वो जो छोटा सा change किया. What I'm expecting कि एक simplified है, एक non-simplified है, right? And I'm expecting कि मेरा जो output है वो same होना चाहिए, coverage same होना चाहिए.
नहीं.
सुनिए, मैं बता रहा हूँ. मैं क्या बोलना चाह रहा हूँ एक बार सुनिए. What I'm trying to say, I will tell you. Just a minute. I'll delete this thing because I have just focus on my goal coverage, even not test cases. Same चीज मैं यहाँ पे करूँगा. Just a minute. नहीं, मैं एक सेकंड, मेरा आप एक बार सुन लीजिए. मैं आपको जो क्वेश्चन है, why I ignited with this, I will tell you. ठीक है? Now the thing is, जो with logical operator है, right? Here, C is greater than 90 is getting evaluated and shown that this is covered.
See, boss, this is symbolic computation. Don't say evaluated.
Means checked. Okay, it is checked.
It checks completely.
नहीं, अच्छा ठीक है.
The thing is that basically it's because the condition basically it's a vacuous. It can produce value for C. It doesn't matter independently for this thing.
नहीं, what I'm saying.
Cement, so the definition
Here you can
need to hit in one case you need to.
What is it saying? Condition coverage is each and every atomic condition has to take both possibilities.
What is CBMC saying for definition? When you say satisfied, ये जो
Satisfied मतलब covered है.
So satisfied, so C is false and C is true. But satisfied doesn't mean that the cumulative evaluation B equal to 0 and C greater than 90 is true.
It means this is covered.
This case is covered.
This particular is covered with the generation of test case.
Which is fine. Which is okay. इसमें कोई problem तो
नहीं है. correct?
नहीं है.
Now fourth में आइए. यहाँ पे आपको अलग रिजल्ट मिलेगा. ये आपको मिलेगा. ये failed है.
Which is true. Which is correct. Which is correct.
We are not hitting that line.
Yeah.
Correct. Now when I'm computing my coverage, right? How many part I have, let's say, checked and generated test cases?
But this test case will not happen.
Exactly.
Because if B equal 0 hai, but B equal 1 is already set.
There are two.
You will never enter the loop. You will enter there.
To understand what does it say? There are two conditions. One, you need to hit the source line. Source line. And then for every atomic predicate, can you like assign variable on both sides? Is it in the one case, is it hitting the source line? Yes. In the second case, is it hitting the source line? No. That's why the difference.
Okay. My point is, in the logical operator, like we have predicate, it is not.
Don't bring short circuiting in
No, that is what my point is.
definitions of these coverage criteria.
Exactly.
You will have to pay some attention to what those coverage criteria are telling you. When you are checking for condition coverage, it's saying that you take an expression, be it a complex expression, each condition from there, it has to take all possible values.
Correct.
So when you have two conditions conjuncted, A and B, okay, so you have four possible outcomes. True, 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 false, false, true, false. When you check condition coverage, it will try to check for all four. Most time it will say two are possible, two are not possible, because you have already made one condition always true. Okay, so that is what it will tell. Once you go to modified condition decision coverage, what it says is, if you take a complex expression, each condition, independent of other conditions in that expression, can that be made true or false?
Exactly.
And once you mask that, even if you make it true, now the check says, the coverage definition says that, oh, still I should pull out this condition and see that that can be made true or false.
Do you have an input
there
that
it will
hits
say
the
that-
source line and is making this particular predicate true? Do you have an input that hits the source line and making this predicate false? That's the definition of the coverage. The CBMC is faithful to that.
CBMC is faithful to the definition of that coverage.
Exactly.
It's something that you have
Okay,
to
no,
understand
I
so that
agree if it is not
Coverage
obeying the short circuiting. That is what my
That's what
point
it
is.
It's not
by
even in the
definition,
picture.
what MCDC is saying is,
अरे बाबा मेरा एनसीडीसी है ही नहीं, मेरा सिर्फ
MCDC
कंडीशन है,
But बिना
No,
MCDC के भी
वो बता रहा है, हाँ.
Exactly, it's saying
नहीं 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 नहीं,
exactly.
no, the thing is with predicate or without predicate. Okay.
MCDC do not say MCDC is not defined based on property. It's a language.
Going to go. You want to give the talk? Distribution testing. Huh? Okay, I think he's been inside the whole day since morning. Very well. Okay. Not been disturbing anyone. Huh? Okay. No, it's been fairly cool. Oh, yeah, so then she is used to. But I think somehow, yeah. Sat. Do I have to join some Zoom? No, I don't think you have to do anything. Right now. Yeah. No, this is fine. Go to the. Correct. There's some Zoom meeting that's going on there. And that's how they're projecting what is on the screen and that's projecting what is on the camera. So yeah, you don't have to do anything. And they will switch to my. It's already there, right? So when you start, it will. Right now it's not showing up. Now can you go there? Can you go to the? Can you go to the browser? No, I'm not worried about all I want is to see. Correct. Go to the browser. Yeah, okay, that's all I correct. No, and if you go to the browser, you will see whether it's okay. That I will trust. Okay. No. Yeah, I'm just saying that you will know whether it has started or not. Oh, the YouTube thing will start showing these slides. Okay. Okay. Okay.
So welcome back, everyone. So we have Kuldeep here, Kuldeep Meal. Kuldeep is Associate Professor of Computer Science at University of Toronto, and he works at the intersection of formal methods and AI. He's a recipient of 2022 ACP Early Career Research Award, the 2019 NRF Fellowship for AI, and was named AI's top 10 to watch by IEEE Intelligence Systems in 2020. There are a lot more accolades to his name, but in the interest of time, I'll hand it over to Kuldeep to present his talk on distribution testing, the new frontiers of formal methods. Hello, hello, hello. Very slow on battery anyway.
Okay. Right. So thanks a lot, Saurabh. So I want to discuss a line of work that we have been doing for past few years. This has been something that Saurabh and I started working on in 2015. So it's been quite a few years trying to develop underlying ideas and all. And along the way, we collaborated with Priyanka Golia, who was PhD student, Yash Pote, who is a PhD student right now, and of course, as with most of my collaboration with Mate Sus. And over the years, these are the 4 papers that we have published on these ideas. And what the reason I wanted to talk about is I'm really, really excited about this topic. And I think there are lots of opportunities to, there's a new problem space. There are lots of opportunities to develop theory, algorithms, and practical and systems that can have practical impact. So there is opportunity to work at the intersection of these areas and with real possibility of real impact. So to put, I know the title may not be familiar to a lot of you. So I'm going to talk about an area called distribution testing. And I'm also going to talk about that why I think this is an area where formal methods there's a lot of opportunity to apply formal methods and lots of problems that formal methods communities should focus on. And before I get there, just to set the context, I'm going to give kind of my biased view of history of computing. And it, as Clark mentioned on the first day, goes back to Turing thesis, and the architecture on which we rely on is the von Neumann's architecture that was proposed. And when it comes to how the key concepts were developed, so the Scott and Rabin talked about the finite automaton, and one of the important breakthrough there was this notion of non-determinism and understanding its power compared to the deterministic behaviors. And based on this model of computing, Floyd and Hoare worked on assigning meanings to the program that can allow one to automatically reason about these programs. So these are the Hoare triples, where you have a precondition, a statement that leads to a postcondition. And of course, then linear temporal logic was introduced, model checking came in, and that has led to a lot of effort over the past 30 years on different techniques for reasoning, BDD, SAT, and beyond SAT. But the key underlying idea that has been around is that in all these cases, when it comes to proving reasoning about the behavior of a program, we are really trying to find an execution of the program so that the property or the specification we are interested in gets falsified. And the key underlying property based on which all these techniques are designed is that a single or a finitely many executions suffices witness for falsifiability. So if you want to demonstrate the behavior doesn't hold true, you go to search for something that is easily specifiable. A lot of hyper properties where you want to talk about two traces rather than, or k traces. But there is, as the work on understanding power of determinism, non-determinism was taking place, there was also a lot of work in randomization. And the first power of randomization that has been shown for any kind of decision or problems was, of course, Addis is usually credited for introducing the power of probabilistic method. And in computer science, the first time we saw the power of randomization was in 1976, when we saw that you can check whether a number is prime or not very efficiently if you rely on randomization. And once the randomization's power was introduced, there was effort on putting it in Turing machines and understanding the complexity of probabilistic Turing machine. And very soon after, the notion of hash functions was discovered in computer science. This is a notion that has been rediscovered lots of times. And the first probabilistic counter was proposed by Morris. And since then, in computer science, when it comes to algorithmic design, everything has changed. Randomization is a very core ingredient in distributed computing, cryptography, streaming, all kind of different applications. But something that I want to highlight here is randomization became kind of the first, a key ingredient or the first class citizen, long after we had formalized the way of reasoning about at least the Floyd-Hoare semantics on which a lot of the model checking effort has been focused on. So randomization didn't even exist in computer science until then. And when we have randomization, the question is, well, how are we going to test and verify randomness? So here is something that continues to occupy my brain quite a bit, which is that how do we know that Python's implementation of random is correct? I'm going to talk about a very constrained setting. In particular, we are going to focus on samplers that are used in testing to generate distributions, and we want to know are these samplers generating the distribution that we care about. And the challenge is that when it comes to randomization, a single execution doesn't suffice. And from complexity perspective, the problems that used to be NP hard suddenly become Sharp hard once you add randomization. So one question to ask. So this is in the setting of finite. Everything is finite here, and the problems suddenly make a big jump in complexity. So is there some hope? And I would like to argue that there is, and I think there has been a very interesting line of work that has happened in theoretical computer science community in what's called distribution testing. So what is distribution testing? There's a very nice survey by Cannon who argues that this is the field at the intersection of property testing and statistics. So as I mentioned, I expect this topic to be very new to most of the people in the audience. So I'm going to talk about different aspects. The first is, what does the distribution look like in the real world, things that we can reason about. What kind of properties we want to reason about, and then can we build practical tools, and does all of this effort pay off? Is there any impact possible? So let's talk about the first aspect. What kind of distributions exist in real world? One setting that is very common to formal methods community is in case of testing, you randomly generate a set of constraints and you want to generate samples that satisfy this set of constraints. So a sampler takes a formula as input, and it is expected to, let's say we are focused on sampler that give random solutions as output. Of course, these days there's a lot of work on probabilistic generators. In particular, here is kind of one model. You can think of a circuit where you have input and the outputs it's generating are probabilistic outputs. And now this model can capture lots of things out there, where you can say that the distribution over the output is defined by the randomness of the input. In today's talk, I'm going to focus on the first aspect, which is samplers. In case of samplers, a sampler takes a formula as input. A set solver would give any of the solutions, but here we are interested in generating a solution uniformly at random. I think this will be a good point to stop and ask any questions if the first part is clear what a sampler is supposed to do, because the rest of the talk is going to be about testing these samplers. Okay, in case of circuits, there's a circuit that the phi is the formula that describes the behavior of circuits. So X are the inputs and Y are the outputs.
X comma sigma is like evaluates to true or false, or what is it?
Phi X, yeah. So it's a formula. So phi X comma sigma is a function on X. And what we are interested in, it captures all the assignments over X so that the output is sigma. Okay, a bit about samplers. I mean, just finding a solution is a hard problem, but at the same time, it's an important problem in practice. So there has been a lot of work for past 4 decades on designing samplers. But only in kind of last 10 years, we have managed to have samplers that have theoretical guarantees of uniformity, in the sense that samplers will be able to prove that the distribution they are generating is what one would like. However, their performance is still lags far behind compared to what you would expect, what you would want in practice. So the setting we have right now, we have systems that can scale to some small instances. So they are very slow. And since they don't suffice for practice, so in case of practice, people have to rely on designing system based on heuristics. Heuristics are often based on Monte Carlo, random walk, local search, and so on. And now we have these fast samplers that are out there, which are used in the practical applications. So on one end, we have these slow samplers for which we have the theoretical guarantees, and we have these fast samplers for which we don't have any analysis.
So in this talk, I'm going to consider three samplers. So the first sampler is a sampler with guarantees of almost uniformity. The second sampler has very weak guarantees. You can talk about that it will output every solution with some very loose lower bound. And the third sampler has no guarantees. It's very fast, but has no guarantees. When we were initially trying to develop these ideas, so it was kind of nice because in 2018, the third sampler, quick sampler, was proposed. And the authors also expressed that they are not able to test whether the sampler is good enough or not. But they had to do some experimental studies. So what they did is take some formulas, generate few solutions, and do standard statistical tests like chi-square and all. But these chi-square tests and all are sound only if you generate lots of samples. So in particular, you need the samples to be somewhere close to the order of the support. So since they couldn't generate so many samples, they said, well, based on the samples we have generated, here are results. But these results are, of course, unsound because it doesn't satisfy the requirements of chi-square test and all. And they said that we are not able to distinguish between these three samplers.
What do the guarantees look like?
It's just that every solution will be output with some non-zero probability. Yeah. So very weak. So I think that also motivated, can we develop some algorithmic procedures that can distinguish between these three objects that are already out there? Right, so that was the first part. What kind of distribution? There are lots of distributions, but we are going to be focused on this one setting, which is a big industry. There are lots of tools out there that generates constraints that are constraint samplers. They generate samples given this for set of constraints. So what kind of properties one cares about? So, well, the first is, as I mentioned, this is one setting I'm talking about, but you could see very often you can have access to a fast sampler and you can have access to a reference sampler, but that's very, very slow. And it would be nice to check if this reference sampler is as good as the fast sampler that you have access to on some set of constraints. And this is equivalent of the equivalence checking problem. So the equivalence checking, you have two programs. You want to check the equivalence. Here you want to check if these two samplers are equivalent to each other. Remember, they generate distribution. So the distribution generated by them are close or no. There are also lots of other properties that are of interest. So for example, you have a distribution, you want to know the support of the distribution, which is all the points over which the probability is non-zero. Some other settings where we have focus on, if you look at the generative models, you want to compute the entropy. This becomes important in order to argue for quantified information flow. So again, you have a distribution, and one of the key properties is the entropy of the distribution. Yeah. No, these are different properties. Yeah. Both would be of interest. Right now, we are just trying to see if they are close or far, but that's also of equal interest. Yeah. So these are there any questions? I know these are very new concepts, so please do ask questions. Right. So in this talk, I'm going to focus on equivalence, where we want to check if two samplers are close or not. When it comes to talking about distributions, there are lots of notions that define distance between distributions. So I'll discuss what we have been doing. I'll also provide some reasons for it, but of course, there are a lot of other notions that are out there to study. So here's one notion, it's called d-infinity distance. So what is it? If you take two probability distributions, so for every point you compute their probability mass and you compute what's the maximum difference. Okay, so you can think about probability distributions. You can describe them using two vectors, and coordinate wise you want to find the maximum difference. Why do we care about this? Well, when it comes to designing samplers, this is often what we end up proving. If we manage to design something that has is close to uniform, then we are often able to prove that it's close to uniform in d-infinity distance. So this is what we are often able to design. There is a relaxed version of the distance, another distance that comes across relaxed. I'll talk about why. So here is what we do here. Instead of computing the maximum difference, we are interested in computing the average difference. So you sum the distance over all points, and that corresponds to the average. And this notion is called L1 distance. There are reasons for it, because you can think of LP norms of the vectors and all. And also it's called total variation distance. There's a very good reason to consider this, and it turns out to be a very powerful and a well-known observation in lots of areas. But I want to tell you, the first time I learned about it, I was amazed by it. So here is what it says. Suppose you have some an arbitrary program, and that relies on getting samples from a distribution P. Complex program, we don't know what it is doing. And all you do is to replace P with Q. And this program has, it's randomized, it's a program that relies on randomization. So there are going to be probabilities of bad things, the program giving errors, or any bad event we define. Okay, so if it was, so consider any bad event that we define. If it was something to catch the bugs, what's the probability it doesn't catch a bug, So if we replace P with Q, then the probability of bad event that would happen would increase at most by the DTV, the total variation distance between P and Q. And this does not depend on what the program is doing. It's a black box result. Yeah.
Here, the program sample only once from the distribution, and based on that result,
yeah. So, and if you do multiple, it's just summation over the number of times you are sampling. Yeah. So this is really powerful, because it says that I don't have to worry about if I had put in Q instead of P, I know how different the behavior is going to be. Yeah. The total variation distance is on the two distributions. Yeah. No, at most. So the bad event can at most be increased by DTV. Oh, this is not. So it's actually, the funny thing is that it's not at all obvious in our area, but in some, the first time I learned from a colleague in cryptography, he couldn't believe that I don't know about this. This would be, similar to someone not knowing CDCL exists for us. So you're right. So it's not at all obvious. There are arguments for it, but it's a very powerful result. And this is kind of bread and butter for the community. Huh? No, bad is just like I just told some bad event. This is any event. Bad is just a name for it. Okay. So here's the thing. The way we went about, and this is also different from classical distribution testing literature, where we have an asymmetric notion of. So what we want is we would like to accept a sampler if it is close in the infinity, because that's what you design. And if it is far in DTV, we want to reject it, because if we were to use it, it would cause us a problem in whatever system we are building. So the asymmetric notion here. So we want to accept something that's satisfy this more restrictive condition. We want to reject that's is more relaxed according to more relaxed condition. And the reason is the accept corresponds to the cases what people design. The reject corresponds to the cases that we cannot. If we put it in our systems, they will cause issues. Yeah. So, I mean, you can compute it based on the, if you understand the full behavior, it's just two probability distributions, right? But black box, that's all we know. Yeah. Oh, yeah, there are lots of metric, lots of things out there to do. This is what we have gone along with. But we have some work that are considering different notions. But this is the notion that I think is also very relevant for the formal methods community, which is, yeah.
Yeah. So if the notion of bad was that, this assertion is getting violated. Now, if you know that this distribution Q, so P was happening, you have a distribution P on the inputs, and that is giving you this assertion violation with certain probability. Now, this result, if you know that another distribution Q, which has this property, is going to increase the probability of the bad event by a certain amount, then this is like an error amplification. This is like, you start with the program and you want to check whether it is this thing or not. You kind of, by feeding this other distribution, you're now increasing the probability of this thing. So if there was a bug in the program, now there is even greater chance that there is an error in the program, and then you'll be able to catch it. Is this?
No, it says that if there was a bug, what's the probability we would catch the bug? And in this case, it would be the other way. The probability you would be able to catch. So what's the probability you won't be able to catch increases? So the probability that you will be able to catch would indeed decrease.
Oh, then if the other way around, then if it was the other way around, because the probability of the bad event, which is the violation of the assertion,
yeah,
that would, let us say, if that increases, then it is a good thing, because then.
Yeah, so it's only, you can argue only on one side. Yeah. The difference is at most this. So when it comes to reasoning, then you can only argue on one side.
Mm-hmm.
But really what it means is that if you substitute P with Q, you wouldn't pay more than the DTV. Okay, you don't care about what the program is doing. That's all we can guarantee. Right.
Yeah, so over there, the checker could also neither accept nor reject the two distributions, right? Because you've used two different metrics.
Yeah, very good
comparison.
question. So we want it must accept if it's close in D infinity. It must reject if it is far in DTV. We don't care what it does
in between.
In between. It will, of course, output something, but we won't penalize it for it.
Okay.
Yeah. And it turns out that from distribution testing, you need some gap. There are reasons for it. You can't. No, I mean, usually the programs do give, accept or reject.
But what if it's close in D infinity and far in DTV?
Yeah, so the algorithms that I'm going to talk about would work only if in the parameters you specify are, epsilon, there's a gap between the two. Yeah. But that can happen. These are two different notions, so you can. Well, it turns out there's a bit of this averaging thing. Yeah, so you are right, but let's talk about this small minor technical thing here. All right, so here's our problem setting. We have a formula, we have a reference sampler that has rigorous theoretical guarantees. We have spent a lot of time trying to build these, but they are slow. And we have a fast sampler, and we want to check if they are close or far. Okay, this is our problem setting. Okay, so I talked about how do we go about designing these practical testers, and this is where first let me kind of give intuition about why this problem is really hard. So we have a uniform distribution, and let's say you design another sampler, and this sampler turns out to be really bad. In fact, it doesn't even sample half of the points of the support. Doesn't even sample half of the things. You don't know which half, but I promise you it doesn't even sample half of them. So a really terrible sampler if you think about it, right? And if all you can do is to just generate samples from it, I'm going to use some of the notation that come mainly from the distribution testing community. So you can allow, if all you do is to generate samples, then until you have generated square root many samples. So what you can do to figure out something is uniform or not. If something is far from uniform, you will get collisions. You will see repetitions. That's the only thing you can do. But if you just generate samples from both of these, then until you have generated square root of the support many samples, you won't even see a collision. All you will see is unique strings, unique samples. Every unique sequence is as good as any other. You can't distinguish between the two. In our setting, the formula phi, the domain is 2 to the n. The number of solutions can be very large. Square root of that is 2 to the n by 2. It doesn't help us at all. So this is not going to work. Of course, this was identified long ago. And my co-author Saurabh Chakrabarty, along with his collaborators, about 10 years ago, introduced this model called conditional sampling. So what is conditional sampling? It said that, well, instead of just giving him black box access, can you allow me to change the program a bit? In particular, can you allow me to sample conditional on some set? So what it means that you will output samples that are with the probability P of sigma, and the denominator is only over the sigma that lie in this set. So I was thinking about sampling from, let's say, Gaussian distribution centered at 100. Now I want to say, can you sample condition on the value being less than 40? So for all the numbers until 40, it still samples as if it's sampling from the Gaussian distribution, but above 40, it will not generate any of the numbers. Otherwise, it doesn't make any sense. So it has to be. Of course, this model captures the black box model because you can just specify the entire domain. So suppose there is someone has figured out how to allow you to generate conditional samples. So we won't pay the cost for it. Okay, there's an you could sample conditional samples. Then what can we do? So then turns out that this model is really powerful. So let's go back to this pesky hard problem of something so far away. So now what we are going to do is we are going to generate one sample from the reference sampler and another sample from this the sampler that we are testing. So let's think about what happens with sigma 1. So the sigma 1 that we are sampling from the uniform distribution, with probability half, it's going to be one of the points that A doesn't even generate. And now we will ask the sampler we are testing that, can you sample just condition on these two? So if it is implementing conditionally faithfully, and one of the points, it doesn't even output. So it will be as if suddenly we have a two-sided, both the sides are heads of a coin, and we are tossing it few times. If you toss it few times, if both sides are heads, after a few coin tosses, you can say that this is really far. So if it is implementing conditioning faithfully, then all we had to do is generate one sample from the reference sampler, another sample from the sampler that we are testing, and say, generate sample condition on these two. I think this is kind of so what are the samples going to be conditioned on these two? So look, the sigma 1, the probability with probability half, this is 0. So it's only going to generate sigma 2 again and again. So with probability half, we'll reach a situation where it's only going to generate sigma 2 again and again. Yeah.
Is there a chance the sigma 1 is in the same distribution?
Yeah. So what you do is you repeat few times. Exactly. So the chance is half. You toss it few times. Yeah. T is a 0. Let's not worry about it. Okay. You can define it in many ways, but all of them are error. And how many samples we need only depends on this closeness and farness parameter. It doesn't depend on the domain. So we went from something that had exponential dependence on the number of variables that we started with. Remember, our support is exponential in the number of variables of the problem we care about to this constant. The amazing thing is that this simple algorithm works, can be argued. We were just talking about a distribution that was really far and we could immediately see, but this works for every distribution that is far. The simple algorithm. So this was about 10 years ago. Saurav and I had met accidentally, and we thought that can we try to make it work in case of. That's a good point. So that's what we tried to see, that can we realize conditioning model in practice? Yeah.
Said that A phi of sigma 1 is much less than A phi of sigma 2.
Yeah.
These are probably.
Yeah.
So what exactly do you mean by much less than?
You can say like take the ratio and the gap is, some polynomial in N. Yeah. Yeah. All definition of much less would work. Yeah. Okay, so can we try to make it work in our setting? So, well, in case of sampling, what does it mean? In case of constraints, what is conditioning? Well, conditioning is adding a constraint. That's what conditioning means. You start with a spaced domain and you condition on adding constraints. So all we can do is that we could construct this new formula phi hat and give it to the sampler and ask it to generate samples from phi hat. What is phi hat? It's phi and x is set to one of the two values. The only issue is that if you give phi hat to any sampler out there, and if it has two solutions, here is how you generate uniform samples if the formula has two solutions. Enumerate both of them and randomly generate one bit that decides which one you output. So every sampler out there always behaves uniform on formulas with two solutions out there, because the algorithm that I told you is the best algorithm out there. So this situation is a bit like if you follow what the car companies did when it comes to testing. If you start testing the sampler under this conditioning, every sampler immediately becomes a uniform sampler. And you put them in the wild, they continue to do what they want. But if you test it on the set of two samples, it's going to be uniform. So what we needed is we want to need a way to construct formulas whose solution space is large. We can't just work with an arbitrarily large solution space because we'll go back to the setting we were in. So we want to construct a formula whose solution space is large, but somehow there's a way to map every solution to sigma 1 or sigma 2. We want to construct something that is large space, but the number of points that map to sigma 1 and the number of points that map to sigma 2 are equal. So this led us to design this notion of kernel, where given two formulas, we construct another formula with a very large number of solutions, but you can always map every solution to sigma 1 or sigma 2. So you just add extra variables, make the number of solutions very large, and then on the original set of variables is either sigma 1 or sigma 2. But the trouble is, how do we know that the sampler's behavior on this new formula is as if its what its behavior would be with respect to conditioning? And this is something that we had been stuck for a long time. And so our solution right now is this assumption. So we call it a non-adversarial sampler assumption. So which is to say that, well, the distribution of the sampler on this phi hat, if you project it on the original set of variables, is what the conditioning distribution look like. If the sampler is uniform sampler for every formula, so if it is truly uniform, then it satisfies this assumption vacuously. The only trouble is that the sampler may not be uniform, but can always fool us every time it's working on the phi hat. We are going to see in experimental results. This is where experimental results will provide some evidence whether this is a good direction or not. We are going to compare different samplers and we will see how well they do on our test suite. Okay, but there is a potential for sampler to fool us. Yeah. 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 Yeah, so every solution, if you project it on the original set of variables, then it's only sigma 1 or sigma 2. Yeah. 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 Exactly. Yeah. So that's kind of, you don't want completely different formula because maybe the samplers work on one style of one structure of formulas. So the formulas have a similar structure. It's a fairly informal hand-wavy argument, but the way we construct is that it won't be completely very different formula. So just adding more clauses and they have a similar, yeah. Oh, that's very trivial. Yeah. The game, no. The game is to make sure that if something is not uniform, then we'll be able to catch it using phi hat. If something is uniform, then its distribution on phi hat projected on X is still going to be, with equal probability sigma 1 or sigma 2. But it may happen that the samplers out there always detect that there's a phi hat and they behave in an adversarial manner. They again become uniform. So remember what was the problem we started with? We could have given everyone phi hat here, right? But it immediately becomes uniform. So the challenge is how will the samplers in practice perform on this phi hat? Okay. If they were not uniform, they shouldn't become uniform on phi hat. It's not, but that doesn't imply, yeah, exactly. It only says that if it's a uniform sampler, everything is okay. So what this allows us is that we can build on the theory of Kohn model, this conditioning model. Right, so putting all of this together, we have built the algorithm and the implementation with it. And what it gives us that if something is close, then we are going to accept. If it is far, we are going to reject. So if it is far and if the non-adversariality assumption holds, then we are going to definitely reject. And in the other settings, we don't know. And the complexity is independent of the number of solutions of the formula, the number of calls we make. So it is a constant that just depends on the epsilon eta parameters. Okay. So now, as I mentioned, the proof of pudding is how well it does in practice. So again, these are the three samplers that we started with when we were doing the first version of the paper. At that time, these samplers were out there. So we performed the comparison of these three samplers. So here's what happens. On the first column is the instances. The second column is the number of solutions of these instances. So you can see the number of solutions is in the order of 2 to the 60 and so on. So very large number, 2 to the 70. The next column is whether we output accept or reject. So here's a sampler that has formal guarantees. So this gets accepted all the times. The search tree sampler is rejected just after 250 samples. So after 250 iterations, we are able to reject it. And the results don't change for the quick sampler also, this set of benchmarks. It also gets accepted on some benchmarks. I'm just showing few benchmarks where it gets rejected. So now suddenly we could distinguish between these samplers. The sampler with guarantees is accepted. The samplers without guarantees, in this case, are rejected. I do want to qualify that just because an algorithm doesn't have guarantees, it doesn't mean that its behavior cannot be uniform. It's just in this case, we could reject it, which also corresponds to it not having the guarantees. Okay. In order to accept, you have to kind of do lots of runs. And you have to generate about 1 million samples in this algorithm. And then you say, okay, it didn't fail any of them. In order to reject, you can reject it the first time it, remember these coin tosses. The first time you see something suspicious, you can reject. Yeah. So this is kind of the first iteration. So it just gets rejected in the first iteration. Yeah. All right. So I think this is where, what we have done so far, we have built some tool algorithm, but you can say, I always knew there are two samplers without guarantees. There's one with the guarantees. The one with guarantees is slow. So what does it give? I'm still stuck to using the one that works in practice. So long ago, when Saurabh and I were discussing this, Mate happened to visit, was in Singapore, and he said, oh, you have something that can tell me yes or no? Then I'm going to go and modify my set solver and make sure your binary outputs yes for my set, my modification of the solver. So, ideally, we would like to have a sampler that's as fast as the other samplers out there, which were rejected. It should be accepted. And, if we can also show that it also has impact on downstream applications. Okay. So as, Mate goes by, here's a solver, cryptomini set. This morning he mentioned 50,000 lines of code. He understands what to do. So he has this access to the binary, which keeps, if it rejects, then based on it also tells you the sample, the assignment that it figured out was far. Based on it, he went and kept on playing with his cryptomini set and has done a bunch of things. I think Mate can talk way more about it. So, restart with static intervals, turns off some of the pre-processing, and changing the polarities, branching on the variables, and so on. So there is something I want to add about. One, it was possible because we had this binary that could reject the early variants of the sampler, and it would also give a witness. A witness right now is one solution, and that we started with. So you could use it. So that's how the parameters and all were decided. There is no theoretical analysis for this sampler. So I had spent a decade trying to design samplers with theory. I'll come back. Right now it's the witness sigma 1 and sigma 2 that we generated and we ran through. So that's. So we didn't even attempt to do any theoretical analysis. We don't know how the set solvers work. A modification of these solvers, and in order to argue that it can generate some distribution, that was way beyond even our hopes. So there's no theoretical analysis, and we didn't even attempt to do that. Okay, so let's see how well it works. The first is, runtime performance. So if you take crypto miniset and you tweak things in it compared to other samplers, it's very fast. Okay, these are the cactus plots, but here's simple conclusion. It's really, really fast. That's not hard to do because anybody can tweak the solver a bit and have it faster than the samplers out there. Well, not anybody has. So how does it performs on these benchmarks? So the benchmarks that Mate had access to while tweaking were not the ones we had tested on. So you can think there was a training procedure going on with these benchmarks tweaking his sampler. This is separate set of benchmarks on the test. So the quick sampler was rejected on all the 50 instances. STS, the search tree sampler with weak guarantees, gets accepted on 14. The Unigen is accepted on all the 50. The CMS then is accepted on all the 50 instances. Okay, so, well, sure, now we have a sampler that gets accepted by this tool, but does it lead to any improvement in applications that if you were to plug it in? So we tried it on 2 applications. The first is a functional synthesis application on which there were lots of talks this morning, and the approach that we have been developing over the years of Manthan uses samplers. So we could plug in any sampler that we want. So now we can plug in CMS in. So the approach, it relies sampling, learning, then counterexample guided repair, and the sampling is a very crucial step here. So we could plug in different samplers. So here's how the performance varies if you plug in different samplers. So this is for the first version of Manthan. You plug in CMS Gen. So the green is the cactus plot. I'm sure Kiran is not very happy about. So solves 350 benchmarks with CMS Gen. But if you were to replace it with quick sampler or just the set solver, it gets down to about 270. So the sampler really makes all the difference in the world. In fact, at that time, that this difference was the only, with quick sampler, we were able to get where the previous state of art tools could do. So CMS Gen made the entire difference in getting to 356. So you want samplers that pass this test, but they should also improve some downstream applications. So that's the first case. The second setting, we tried it on this combinatorial testing. So you have systems with lots of configurations, and you want to test many configurations, and something one realizes on T-wise coverage. So how many combinations of the T subset of features have been seen? So again, this is a well-studied problem. There's in fact an entire community and conference on it. We took the standard suite of the benchmarks, and we tried for T-wise coverage for T equals to 2. And so these are the benchmarks for which there had been a challenge for a long time to reach 100% coverage. So let me tell you how to read this. On y-axis, there's a coverage. On x-axis, there are benchmarks. So for every a point indicates for the corresponding benchmark how much coverage we could get. So the first time Priyanka had identified a potential of this CMSN. So the potential in synthesis then was doing these experiments, and my hunch was that something is wrong. How are we getting 100%? So we reran it, went through to see that we are really able to get the entire coverage. So CMSN here is significantly better than anything out there. Okay, so hopefully I convince you that it can really have impact if we were to design samplers this way, which is of course very different from what I had done for a decade. All right, so just to conclude, well, it was designed having access to a tool that could give the feedback. So at least the feedback is there. How there is still, it requires the expert to be able to tune the set solver based on the feedback, but the feedback mechanism is there. So what I want to talk about, I mean, from the time the basic concepts in verification were designed, a lot has changed. Probability distributions are first-class objects. We need a way to think about them in order to how to test and verify these systems that have probability randomization as key component. There are lots of properties we have barely started. I talked about equivalence, support size estimation, entropy. And I think there's also a lot of hope for building systems and the theory with this gray box access. Most systems, it's possible to modify a little bit. In this case, we looked at this conditioning sampling model. And I want to strongly claim that all of this pays off. We are able to design samplers that are significantly better than what is out there. So in all our projects in our group, we rely on CMSN. For anything we use, CMSN is the sampler of choice. I think we have just started here. There are lots of interesting directions to do. So far, everything that has been built around is just for the uniform distributions. How do we go beyond uniform? Developing algorithms that would work in practice, developing systems, all these questions are out open. It also suggests maybe an interesting approach to design samplers for theories that are harder than SAT. Is maybe perhaps go and design a simple, slower, but something that we can reason about, then use that to design another sampler in a test-driven development manner. So rather than going the way that we tried for a decade of trying to develop theory and scale this further. So there is perhaps an opportunity to go design samplers this way. In many ways, I mean, this is how people write code, whether you like it or not. Nobody is formally verifying the code out there. You test it on a few things, and you think it sounds good, so you put it in the production. So why not do the same for designing samplers? There's still a lot to do to develop the notion of witness, because in case of non-deterministic systems, witness can give you the reason for the failure of it. Right now, the witness is not able to do that. It's going to be very interesting because in case of non-deterministic systems, one witness suffices. Not the same for probability distributions. So how do we develop notion of witness or the sets that I have to go around? And finally, how do we certify that these tools that we are designing are indeed correct? So there is quite a bit of work that needs to be done. I talked about the two tools, CMSN and Barbaric. Both are available open source. Please do try it out. So with that, I'll conclude. I'll be happy to take any questions.
Yeah, thanks, Kuldeep, for a fantastic talk. Are there any questions?
You said that this works only for uniform distributions in that point. You mean it works for non-adversarial distributions, right? And the only one which you know is right now that's non-adversarial is the uniform distribution.
No, the theory needs to be developed. Suppose you don't want to generate from uniform. Let's say you want to generate from Gaussian distribution. In this case, you want to generate from some weighted distribution.
Yeah.
And now how do you check that it is close in the weighted distribution? There is, in theory, you can make it work, but the dependence is really bad. So it won't work in practice. So there is also the theory needs to be improved of the algorithm.
Yeah.
So suppose the reference sampler is generating from some distribution, weighted distribution that's not uniform, and
Yeah.
you want to check the closeness with respect to it.
Yeah. And also,
And of course, also it has to be not. Right now, we can only handle the non-adversarial case.
Yes.
We don't know how to check if a sampler satisfies the non-adversarial assumption.
Yes. And also, like if you could go back to the slide on kernels. Yeah, so I think one way of creating a kernel would be to add a clause that x equals sigma 1 or x equals sigma 2, and then for the new variables, just add a bunch of tautological clauses for those variables, right? Is that would that work?
So most samplers would immediately figure out if there are tautological clauses, they will set them uniformly correct. What you can do, and which is what we have gone on to do, is you could say that, well, the CMSN is doing very well, so maybe I should harden the kernel. So this was Mate's idea. So what you can say is that I'm going to say that if x is sigma 1, then it implies some simple formula on new set of variables. And if x is sigma 2, it implies some very hard formula, some cryptographic formula. So if a sampler is truly uniform, it would still, I mean, it may take a long time, but it will still continue to behave uniformly at uniform. It will continue to behave like a uniform sampler.
Yes.
But, a sampler based on the set solver will, will go say, okay, this is a very hard formula. Let me go back, restart. And the moment it goes on the easy side, it finds a solution. So you can vary this hardness parameter, and you can see the CMSN's performance degrade and degrade in terms of getting rejected. But then the interesting thing was to observe that, well, maybe there is something to do with the restart. So you change the restart frequency, then you can again make the CMSN behave closer and closer to uniform. But now you start paying off in the time, because now if you don't let it restart, then you pay off in the time. So there are lots of space here to explore kind of the sweet spot between, how good sampler you want and how fast sampler you want. Right now, a lot of this is really using Mate as the automator, but it would be nice if to automate everything through the code. So yeah.
Yeah, so I wanted to ask regarding the same slide itself. You're mentioning this non-adversarial assumption, and you're also saying that this phi and phi hat has similar structure. So is it the case that so firstly, what do you mean by similar structure? Because is it the case that, like, depending upon whether it's similar or not, it will be either non-adversarial or not?
Yes, it is. I mean, we don't know how to test it. So right now, we also don't know how to formalize the notion of testing whether it satisfies the assumption or not. But one thing is very conceivable. I mean, if you think about the samplers you design samplers just the way we design solvers for some kind of formulas. So if you have a formula with very different kind of structure, you may say, I don't even care about those formulas. So don't test me on those kind of formulas. So it would be very unfair to test on a kind of formula that I don't care about. Since you are designing these samplers based on heuristics, so you don't want them to be completely different. But yeah, it would be interesting to even understand, characterize, given a sampler, what kind of non-adversariality assumption it satisfies. So right now we just assume that it's non-adversarial. Okay. That's an interesting direction and would be nice to work on.
Okay, thanks. Another question that I have is you say that in this Manthan, just replacing the sampler was a huge improvement. Do you have some intuition as to why that is the case? What actually goes wrong with the wrong sampler?
So I think in the morning, Priyanka talked about in Manthan, you generate samples and then you learn decision trees. Well, if you are learning trees on the samples, so if the samples that you have are bad, then you won't learn good functions. So, this would be kind of garbage in, garbage out. If the samples are not good, what will you learn over those? So, sampling is a very crucial step there.
I guess one of the reasons you need this, I mean, you're given a formula phi and you're outputting another formula phi hat such that its projection is sigma 1, sigma 2, right? And so I'm just trying to understand this assumption. So is it really saying that the behavior of the sampler on phi and phi hat may be different?
We are hoping that it's not if you project.
Yeah, but this assumption is saying that they are the same.
Yeah.
So what if you did the sampling on phi itself, but then basically mapped back the solutions? I mean, here you're trying to get the solutions as that the mapping is easy. But it's like hashing the solutions into.
It can be, yeah. I mean, that's also.
Because then you're guaranteed that the sampler has sampled on phi. Whatever you're doing is post-processing. You could not have changed the behavior of the sampler.
That can be interesting, but yeah, I mean, that can be an interesting way of. It's still not clear that, you still have to assume that. Yeah.
Yeah, I mean, the mapping itself may be a showstopper.
Because you could say that's subject to the mapping.
This assumption, right?
Huh?
That would allow you to get rid of this assumption.
No, then the mapping assumption you have to still, because it's non-adversarial.
But it's not inside the sampler.
Yeah.
It's outside the sampler. I mean, you're using the sampler to get the samples. And then you're mapping the samples.
Yeah, sure. That's a good point. So there's an assumption in the algorithm that this mapping is known as it's not the easy mapping.
It's not an easy mapping.
Yeah. That's a good point. We should.
So the idea of having this oracle and then just sort of tuning your program till the oracle is happy, I think that's very clever. I wonder if there are any other problems you could apply that approach to. Have you thought about that?
No, I think, it would be. This is where we have done, and right now we want to see if we can do it for SMT and CSP, and because designing something slow that's good is hopefully not too hard. Yeah. It would be nice if we could solve every kind of problem through this way, but yeah.
So perhaps you might have covered it, but when you say similar structure, what's the measure of similarity here?
We don't have a formal measure. It would be very nice if we could formalize. So this is the part that took us about 3 years trying to argue with each other what makes sense, because the obvious step doesn't work. That we implemented and did not work. From here to here was a lot of, what would make sense or how to come up with it. And still, it would be nice, I think there are some very interesting questions. Can we formalize it much more? Can we characterize the complexity of checking if it satisfies this assumption or not? Yeah.
Okay. So, yeah.
Yeah, so there will be a photo session, group photo for the workshop. Yeah. So it will be held here. This is steps right next in this side. So I request everybody to, we'll move, just all of us just go there right now and finish this quickly. And of course, there is coffee tea behind.
Yeah, let's thank Kuldeep for our contest.
Sampling, but then, yeah, that is a very good. Yes, but that, I mean, that we kind of develop. Yeah. That's kind of.
Go running. He's doing yoga. Yoga up there.
He knows more Sat+Smt than us.
Outside.
Yeah, that's easy. Is it a PDF? Yeah.
Okay, welcome back. So this is the last session of this year's Sat+Smt Winter School, and we have Clark Barrett with us, who of course gave an excellent tutorial on the first day on SMT solving. So Clark also happens to be the director of the Stanford Center for Automated Reasoning and the co-director of the Center for AI Safety. And he and his group have been doing some amazing work on ensuring that machine learning systems, automated reasoning systems actually do things that are not harmful to us. So there's a special talk by Clark on when AR met AI, and I'm sure all of us are looking forward to that.
All right, thanks a lot. Yeah, so I offered to do this bonus talk because I knew a lot of people were also interested in this subject. And I'm going to tell you about a few different things. I'm also really happy with this front slide. One of the advantages of having kids with different talents than yourself is you can pay them to make art for your slides. So that's what I did. My daughter did that. All right. So there's these two areas, automated reasoning and artificial intelligence. And one thing that I think is becoming clear is that they have some complementary capabilities, right? So automated reasoning has now become quite a mature technology. It's being used in many applications, formal verification in industry. And the really great thing about it is it gives you some guarantees, right? So we can just have these nice rock solid mathematical guarantees. But of course, scalability is always the bottleneck. On the other hand, AI has these amazing capabilities. It works really well with messy, ill-formed problems. It's data-driven, but there's this sort of Achilles heel, right? No correctness guarantees, adversarial inputs, hallucinations, right? So maybe there's a way that they can help each other. So you can think of two directions, right? AI for AR, maybe AI can help with scalability. And AR for AI, can you get some correctness guarantees for your AI system? So I'm going to talk about some work in both of these directions. So first, AI for AR. All right, so this is a paper that we had at FMCAD this year, led by my student Hao-Tse Wu, who's a very good student. And the idea, well, here's the idea. So if you want to use machine learning to accelerate some automated reasoning procedure, there's some ideas out there. One is, okay, let's just train a neural network to solve SAT or something, right? Okay, well, you know, that doesn't work so well. It's way, I mean, this thing called Neurosat that Daniel Selsom built, it works way better than you would expect, but it's still, you know, not very fast compared to real SAT solvers. And you don't really have guarantees that it's correct. Okay, but you could also say, all right, let's replace some internal heuristics in the SAT solver by something that we learned. And actually, the best talk I heard on this was by these guys at SAT 2019, this crystal ball work. I thought that was really cool. So yeah, you can do it, and you could spend all the time that they spend on it to get maybe a little bit of benefit. But it isn't clear to me that this is really a huge win. In fact, the thing I took away, and I apologize for if I missed the whole point of your talk, was that after all this work, we learned that the most important features are the ones that are already used in the SAT solver. Yeah. Well, it's nice to get some confirmation, right? Okay. All right, but actually the most successful thing so far has been this meta-algorithmic design, which basically means you take a bunch of problems, you train and you learn what are the right parameters to use, you do this tuning, and then now you have a new way to run your solver that's been tuned to this problem distribution. And there's these tools like Satzilla and other tools that are actually quite successful. Okay, so we thought that's nice, but can we actually improve this a bit? Because first of all, it's not distribution proof, right? So whatever you do to train your solver parameters are based on the training data, and you might come to some new problem that has a very different distribution. So that's a problem with the offline approach. The other thing is, well, we're talking about automated reasoning. And if you have to go train for a week before you can run your solver, that's not very automated. So we don't really like that either. So our idea is, let's see what we can do online. So we call this self-driven strategy learning. And the idea is, suppose that you are given the task to use automated reasoning to solve a set of related problems, okay? And this comes up quite a bit, right? Bounded model checking, you're going to unroll, and each unroll is similar to the last. Maybe you're doing abstraction refinement. Each refinement is a little bit different from the previous one. MaxSat, and so on. So the idea is we're going to narrow our idea of problem distribution just to the problems in the set S and see if we can learn enough from this set to speed up our entire problem set. And the key idea is we're going to collect data and learn a model on the fly while solving S, and hope to do this fast enough that it leads to an overall speed up in the total time it takes to solve the problems in S. All right, so here's the big idea. We're given this set of related problems. We have some space of solving strategies we'll call V. And normally what you would do is you'd say, all right, I have some strategy that I've picked called V0. I'm going to check problem 1. I'm going to check problem 2, check problem 3, etc. With my default strategy. So what we're going to do instead is we're going to say, all right, let's check I1 with strategy V0. And let's add the fact that I1 using strategy V0 has some cost A. Then we're going to check I1 again, this time with some other strategy, and we're going to learn what the cost of that is, and so on, doing a bunch of different checks. And then we're going to fit a model to these data, right? We're going to say, all right, given that I know that problem 1 took this cost with this strategy, I'm going to try to figure out, use the machine learning model to be able to predict what the cost is for a given problem and a given strategy. And then I'm going to take the best strategy for the next problem, and I'm going to use that based on the model. All right. And so on. Okay, well, wait, what about the overhead, right? It was bad enough that I solve all the problems in S. Now you want me to train a model, solve things multiple times. This sounds really bad. Well, what we're hoping is that the data collection time is amortized by the speed up you get by learning this model. Okay, so we also have a little calculus for this. It's not really anything unexpected here. It basically has some rules for iterating through the set, and it has some rules for collecting and training and picking the strategy. Here we are assuming that this set of related problems, what you're looking for is a satisfiable problem, right? So you're going to basically go through until you find something that's satisfiable, then you're going to stop. Of course, there are examples where that's not the case, but this is the assumption we're making. And basically how it's going to work is every time we solve a new problem, we'll collect some data, some fixed number of times, and then we'll train our model. Then as we move to the next problem, we'll apply the strategize rule to pick the strategy. Once we exhaust some training budget, we'll stop collecting data and we'll just solve the rest of the problems. Okay. All right, so we tried this out. We did a case study on bounded model checking. You're probably familiar with bounded model checking, but it can be basically what you're trying to do is you're looking for a violation of a property in a transition system after a certain number of cycles, say k cycles. And typically what you'll do is you'll start with k equals 1, and then you'll increase k and keep looking for violations. And the Sat or SMT problem that you're solving looks like this. You've got some initial state I0. You've got a conjunction of the transition relation for each k, and then you have the property holds from 1 to k minus 1, but the property doesn't hold at k. That's the thing you're trying to see if that's satisfiable. Okay. And essentially now you can say, well, the set of related problems we want to solve is the instances of this formula for all the different values of k. And we're also going to add in a step size, because it turns out that most of the time you don't want to increase k by 1. You maybe want to increase k by 5 or 10. That can really speed things up. Okay. So we tried this on the unsolved benchmarks from the recent hardware model checking competition. And we used KISSAT as our solver. And so we're going to compare KISSAT solving the BMC problem to the SDSL version of KISSAT, where we're tuning the strategy. And the strategy space is actually quite interesting. There was a paper that Bruno Dutertre wrote where he said, for KISSAT, these are the parameters that you want to tweak. And turned out, this turns out to be quite useful. We have some details. We actually use some sampling. Maybe we should use your sampling next time. But we're doing some sampling to do the data collection. Our machine learning model is a very simple one. It's just a tree ensemble. And each job is given 2 hours. Okay. So this is the big punchline. All right. What happens is if you run the vanilla bounded model checking, you get the blue line, which as you increase k, quickly goes exponential. If you use the self-driven strategy learning, you pay a little bit of overhead at the beginning, and then you get a flatter line going on to bigger unrolls. So once you get up to bound 35, you're actually solving it twice as fast. Okay. Yeah.
It's surely a explore, exploit sort of trade-off, right? And how do you decide?
Yeah, I mean, there's a lot you could do. So what we did is we just fixed a percentage of, we sort of we projected how much time we were willing to spend total. I guess we had a time limit, 2 hours total. And we took a budget. We gave it like 10, 20% and said, you can train until you exhaust that budget, and then you just go with your best strategy after that.
So this is like for a given problem instance, or you train to some instances and then said that
We didn't do any training. No, so the training is all done on the fly. So it's basically you're given a problem instance, and then you want to solve all the bounded model checking problems. Those are your related instances. And so we do all the collection training on the fly as we go. And then once you exhaust your training budget, you just solve the rest. Yeah, so the little bump there is the price we pay for the training. Yeah. Right, that I think that's the parameter space. So I forgot how many. What's that? No, so there are many options in KISSAT, but if you read that paper by Bruno, he identified a handful, maybe 8 or 10, and then if you take the possible values for those and multiply that together, you get 8192. So that's how the total number of strategies that we considered. Yeah. Okay, and basically, in over 90% of all the benchmarks we tried, you get a better bound. So that was pretty good. Right, and this is just comparing against the other solvers in the competition. The AVR was the one that won. Our solver Pono took second. And basically what you can see is that with the self-driven strategy learning, we actually get 7 unique solves that none of the other solvers got, plus the time was quite good. Okay. So this work was just one example of, let's see if we can use a little bit of lightweight machine learning to accelerate an automated reasoning problem, and it actually worked out pretty well. And so I think there's a lot more that can be explored in this direction. So that was the first thing I wanted to tell you about. All right, so the other piece is where I've done more work, which is let's apply formal methods to the AI space. And what can we do there? So I'm going to talk about 4 things in this area quickly. And my favorite is the last one, so I'm going to make sure I have time for that. But there's also a little bit of a tutorial feel here if you're not familiar with this area, so I'll go over the basics. Okay, so first of all, you probably don't need this slide, but this is sort of how I explain formal verification to people. I say, look, if you want to do formal, you need 3 steps. First, you have to take the system you're interested in and create a mathematical model of it. Second, you have to write a formal specification. What is it that you want to be true about this system? And then you have to prove it, step 3. Now, what's cool is for step 1, if you're dealing with a hardware system or a software system or even a machine learning system, turns out this is actually easy because we know what the semantics are for a programming language. We know exactly what the semantics are for Verilog. So you just have to write a translator, right, from that into some logic. Modeling is way harder if you're doing like cyber-physical systems, right? Now you've got to model the actual physics of what's going on, and of course it's never accurate. So we're actually really quite lucky when we're doing software and hardware and even machine learning that the modeling step is easy. But the specification step, this can be quite challenging, right, for many reasons. And then to do the proof, of course, we don't want to do this proof ourselves. We want to offload it to solvers, and now we have good solvers that can solve many of these problems. So how would we apply this to an AI system, right? So we have a deep neural network. Deep neural network has some inputs. They run through a bunch of layers, do a bunch of math, and output some outputs, right? That's it. That's all machine learning is. It's a bunch of linear algebra. Okay, so how would we verify a system like this? Well, to create a mathematical model, we just need to write some equations that capture what's going on here. So this is actually pretty straightforward. If we look at a really simple example, let's have 1 input, 1 output, and a hidden layer with 2 nodes. We're just going to write some equalities. We introduce a variable for each node, write some equalities that talk about the weights and the sums, and now we've captured, that neural network in a set of equations. Now, that's not totally true because there's these funny things called activation functions, which basically at the end of every layer, after you do this weighted sum, you apply some function to it, right? And a typical function is this rectified linear unit, which just takes the maximum with 0. So if you add up your numbers, you get a positive number, then the result is just that. If you get a negative number, then it just cuts off and is 0. Okay. Okay, so you've got this thing, and the problem is it's not linear. You can't express this with a linear equation and use a linear solver for it. So what we'll do instead, we just split this into 2 variables. One variable represents the input to the activation function. The other represents the output. And we're just going to keep in mind, we're basically going to write down these constraints directly and hope that our solver can reason about them. And I'm not going to talk about it, but basically the first work we did in this area, the ReLUplex solver, the key innovation was basically telling simplex what a ReLU is and say, don't try to do case splitting on it, but instead try to just fix it directly while you're doing the simplex algorithm. Okay, so basically we can model these systems. Now, how do you specify a property? Well, here the sort of simple thing to do is to specify some kind of input-output property about your network, like if the input's within some range, then the output is within some other range, right? And then you can try to check this. So how do we check it? Well, we just feed this to some solver, SMT solver, maybe an LP solver, maybe a specialized tool for this domain. And the solver either produces a proof or a counterexample. And we have, special ways of handling the activation functions and lots of work being done to improve scalability. So when we first started on this, the best, there had been some work maybe 10 years before our first paper. And in that work, I think they could verify something about a network with about 20 neurons, right? That was the limit. So with our work, we got up to 300. So that was great. That was a order of magnitude. And since then, various people worked on it, have improved lots of things. I think we're up to about 10,000, right? So if you've got a network with a few thousand neurons, then great, formal methods is for you. But obviously, there's still a long way to go to handle some networks. So that's okay, because we formal methods people have been in this boat our whole lives, right? We can't solve everything, but we can solve some things. And then we figure out clever ways to use our tools through abstraction or decomposition or whatever you might imagine, so that you can actually apply these techniques. And I think it's the same here. All right, so let me tell you a little bit about what you can use this for. All right, so you've all seen this picture probably a million times. You take some image, you add some noise to it, it looks the same to a human, but the AI system suddenly thinks it's something totally different. Okay, we can specify the property of adversarial robustness by saying that for any point in your input space, if you perturb it by some amount, then the result should not change, okay? And so this is one way to write it formally. And this has been great for all of us writing papers, because we don't have to go interrogate the person who designed the network and say, well, what is this thing supposed to do? We just say, look, you want your network to be adversarial robust, don't you? Well, great, we can verify that. And so we've done lots of attempts on that. One thing that's kind of interesting is certain kinds of fairness actually pop out as a special case of this, because if you have an input space and you want to know whether your output is invariant with respect to perturbing some of those inputs, that's exactly what adversarial robustness gives you. All right. Now, what if your property that you would like to check is not something that can be specified quite so simply, right? For example, suppose you want to take this particular traffic sign and look at it under various shades of brightness. So it could be very dark or it could be very bright. But in all the cases, you want to identify this sign correctly. So this is a little bit more relevant in practice, but it would be very hard to write down formally what this could mean. So how do you specify and verify this? So again, my student Hao-Tse Wu wrote a paper about this, and there's a very nice idea here. So the idea is, rather than having this notion of perturbation where everything is in some radius of a single point, suppose that your notion of perturbation is defined by some data, right? So that basically somebody hands you a pile of data and says, everything in this pile is in my distribution. Can you check that you're robust with respect to that perturbation? Okay, so what we can do is we can try to capture this perturbation by training a deep generative model on the pile of data that we're given. Okay, so we're basically going to have some latent variable. We use the latent variable to tune the amount of perturbation, and we train a generative model to learn to match the data in our distribution. Okay, so now you can take any input image, feed it into the generative model, and it should be able to produce a whole spectrum of perturbed models that match the perturbation that you were given the data for. So great, so now what can we do? Well, if we have some classifier that's trying to classify and we'd like to be robust with respect to this perturbation given by this perturbation set S, then basically we can compose the generative model with the classifier. And now we can write a specification. And the specification just says that the classifier should be robust with respect to perturbations in the latent variable that controls the generative network. Okay? So we've actually reduced the problem back to adversarial robustness, which we know how to solve. All right, so that was a clever idea. And we show that it works for a bunch of different kinds of perturbations on networks that are not too big. Yeah. That's right. So the GAN becomes part of the thing that you're encoding. That's right. Yeah, and actually one of the things that we ran into is the typical generative models use things like sigmoids for their activation functions. So first of all, it looks like you can probably use ReLUs and it still works out okay. But we also came up with a nice CGAR algorithm for working with the sigmoids that works in practice as well. So we do use a piecewise linear approximation of the sigmoid and refine it on demand until it converges. So that's also part of that paper. Yeah.
So you can learn the distribution using a GAN or something, but then how do you ensure that, how do you do perturbation modeling so that it remains in the distribution?
Right. So well, you do your best. Okay. So you take the data you have, you train the model, and then you do the verification. And the nice observation is if you get a counterexample, it actually tells you something very useful, because you can run your counterexample through the GAN, look at the image, and then say, oh, either that's a good image, and that means my GAN's okay and my classifier is bad, or it's a bad image, that means my GAN's not okay and maybe I need to get more data or train it better. So I think the counterexample gives you some information. If it actually is robust, then it's true you don't know everything, but you do know that your classifier is robust with respect to, a large number of images that are in your distribution. So I think either way you get some information. Right, so your counterexample would be just some value of the latent variable. But then if you put that value into the GAN, you can actually generate the input and see if it makes sense. Yeah. Yes, yes. That's right. That's right. Yeah. Yeah, but that input variable could have, a very large domain. Yeah.
It's an input vector, right?
No, it's just a variable. I mean, it could be a vector. So yeah. So you input for the GAN, you input an image and a perturbation factor. And then the factor controls where on that spectrum of perturbation. But you're right, you could use a vector. I mean, there are lots of things you could do. Here we're just talking about, we'll just have some dial that you dial up and down. But you could have multiple dials, sure. Okay, so, all right, so that was one interesting piece of work about trying to address this challenge of specification. All right, so I want to tell you a little bit about some other work where we considered the question of verified explanations. This work was led by Min, and House also helped on this as well. Okay, so the idea in one kind of an explanation, well, first of all, explainability is just the question of you have some machine learning system, it gives you some answer, and now we would like to understand why did it give us that answer. Somehow, and there are lots of applications where this is crucial, where an AI system makes a decision and it's crucial to understand something about why that decision was made. One kind of explanation is to take the input and sort of reduce it and say, well, it turns out that what really matters in this input was this part of it, okay? So that's one kind of explanation, and that's the kind that we'll be looking at here. So you may have heard of systems like LIME and anchors, where they take an image and they just sort of focus on here's the part of the image that really was crucial. The thing about, so these are very nice pieces of work, but they don't actually give you guarantees, okay? So it's not actually true that if you fix that part of the image and change the background, that you'll always get the same classification. It's like pretty close to being true, but it's not true. And in fact, for MNIST, where you're just trying to identify these numbers, it might give you a very trivial explanation. So here, for the number 2, it'll give you an explanation that just sort of highlights the 2, which sounds reasonable. But if you look at the explanations that our formal system gives, it's actually more complicated than that. And the reason we know this is a 2 is not just because of the white pixels, but also because of the black pixels, right? So if you look at the green is the explanation. You actually need this middle part to be black so it doesn't look like a 3. You need this arc to be black so it doesn't look like a 0, and so on. Okay, so it looks like it might be, in some cases, important to get something more than just sort of a rough cut at what the explanation is. So the idea in our VERIC system is we're going to divide the input into relevant and irrelevant sets. Then we're going to formally check whether the output is robust against changes in the irrelevant set. And we're going to try to make that relevant set as small as possible. So there's a quite naive algorithm for this. Basically, you just consider the features in the input one by one. You check to see if holding everything else fixed but perturbing the irrelevant set can change the classification. If not, then you add that to the irrelevant set. Otherwise, you put it into the relevant set and continue. So you might consider here, if you have 9 features, 1, 2, and 3, it's robust. But by the time you get to 4, it's not robust. So 4 is relevant, and so on. Maybe you get 3 relevant inputs, and the rest can all be perturbed, and you still get the same result. Okay, so here are some explanations that we generated using this technique for some traffic signs and for some numbers. So what's interesting is on the traffic signs, you'll see, again, this feature that sometimes the background is more important. But for the arrow, we zoom right in on the arrow. That's crucial. Another thing you can do with this on the bottom right is you can find out which are the pixels that keep me from deciding that this is something else, right? So this 1 is not an 8 because of the pixels shown here. Okay. Now, of course, it matters what order you consider the inputs in. And so one thing we did is we compared if you just pick them in random order, or if you use some heuristic, and the heuristic we chose was sensitivity. Sensitivity just says if I perturb this input, how much does it affect the output? So you want to take the pixels in reverse sensitivity order. So let's see. Right. The ones that are least sensitive are most likely to be okay to put in the irrelevant set, and the ones that are most sensitive you should consider last. And this little chart just shows you that's a good heuristic. So the little triangles are using the sensitivity heuristic, shows the size of the explanation, and then the bars of circles are all the random ones. So basically, we always beat the random one. So that's good. Another thing we looked at is maybe you don't want just a black and white explanation, right? So it could be you'd like to know some shade of how important it is rather than it is or it isn't important. So what you can do is you can change how much you're allowed to perturb the irrelevant set. So if you're allowed to perturb the irrelevant set by any amount, then that's a very strong explanation. If you're allowed to only perturb the explanation a tiny bit, then you still can find out what's robust against that. And so we can build these little images that show the bright yellow pixels. Those are the ones you can't perturb even a little bit. And the darker pixels you're allowed to perturb a lot. And so you can kind of see more detail about which parts of the image are more important. All right. Yeah, just some results. The sort of key result here is with our Varick system, we get explanations that are much smaller than the other heuristic systems, and they're provably robust against perturbations. So those are both nice things. Of course, you pay for it by it costs you more time to generate these. We also applied it to some real-world data on aircraft taxiing. And what's nice to see is that if you look at the explanations on these runway images, they're following the runway line. So whether the line is there or not, the places where the lines usually are is the place that we say are important. So that's good. One other kind of interesting thing is if you use an incomplete formal tool that can answer unsat, but sat might be spurious, you can use more scalable tools, say an abstract interpretation solver that just does bound tightening. And then you can use that for your explanation as well. Now what happens is you'll get a bigger explanation, but it still has the property that you would like, which is that it's resilient against perturbation. So this gives you a way to sort of trade off explanation quality for scalability. So that's nice. All right. There's a few other interesting things that we're looking at. We made an observation that if you have inputs that are out of distribution or incorrect, they are more likely to have a much larger explanation. So we've got some new work that we're working on. How can you leverage this information to maybe get better results from your model? That's kind of interesting. Yeah, there's something else too, but I forgot. Anyway, I think this is an interesting direction. All right, but now this is really interesting stuff. Okay, so we've shown that you can apply some automated reasoning techniques to traditional machine learning systems, do some verification, check robustness, maybe get some explanations. But then, of course, we've all been surprised and astonished by these fancy new AI systems called large language models and all the things they can do, right? And one of the really stunning things they can do is write code. So I'm sure you've all tried this. I remember the first time I tried it, I was really blown away. Well, actually, the first time I was blown away is when my student said, write a SAT solver. And ChatGPT wrote a pretty decent SAT solver just on the fly. Boom, here it is. I couldn't believe it. And then, of course, the first time I used it, I had to write some script to translate something, and I'm not a good Python programmer. And I was like, oh, maybe ChatGPT knows how to write this. And sure enough, within 15 minutes, with just a couple iterations, I had my script. However, it did make a mistake along the way. It wrote some code and it had an off by one error. And, I scolded it and it apologized profusely. But, you have to know what you're doing or some things can go wrong. So, futurists are now saying, well, in the future, AI will write all the code. And I'm like, oh, no. I don't want to live in that world, right? So what are we going to do? Okay, so we have some really interesting work on verifying LLM-generated code. This is with my students, Livia and Ying, and Oded Padon from VMware. So, all right, LLMs are pretty good at generating code. And this actually does have the potential to help us scale up coding tasks. But even if the ML people aren't all worried about this, we're worried about it, right? We formal methods people. How do we know this code is correct? Well, here's a key idea. If the LLM can generate the code, why not also generate the specification? And if you generate that, well, hey, we can check it. We know how to check. Our tools are good at that. So maybe we can have this nice collaboration where the AI generates the code and the spec, and we just check to see if it did a good job. All right, yeah. Ah, yes, you could generate true. So how do we know that's a good spec? Okay, I'll come back to that. All right, so the first experiment was just to see if this is even, if this is a pipe dream or if this could work at all. So we hand wrote 50 textbook algorithms. We asked ChatGPT-4 to generate a formal spec for each algorithm, and then we checked using some formal methods tools. And we did all this with a tool called Daphne that you may be familiar with. The reason we picked Daphne is, even though it has many problems, it is arguably one of the best supported tools for doing deductive verification. So deductive verification is just, we heard about it earlier today. It's this Floyd-Hoare style of verification where you have, precondition, code, postcondition, and then you translate that into logic and check it. If you can do that for every line of code, then you know that the code satisfies the specification. The invariance, it's part of the spec. We asked ChatGPT to generate it. Yeah, we didn't write any invariance. We just say, please give us the spec. Okay, so here's an example. So we say, you are an expert in Daphne. Please fill in the pre and post conditions. And then we give it like a little to fill tag in the code. So here's a simple little program. It just swaps the values of two 8-bit bit vectors using 3 exclusive OR operations. Okay. So of course, ChatGPT can't help but tell us all about it rather than just giving us the answer. But sure enough, in the middle here, it gives us the answer that it swapped the values of X and Y. So what was the result? Perfect on the first try. Good job. Okay, let's try something a little harder. Here we're just assigning some values to some array variables. Okay, that looks not too bad. And in fact, it writes the post conditions that says how those values have been updated. So that's great. But we send it to Daphne, and Daphne complains. Says, oh, you are modifying an array element. You need to use a modifies clause. So this is just a feature of Daphne that if you modify an array, you have to actually say as part of the spec that this could modify an array. All right, now this is my favorite part of working with LLMs, is how they immediately become an expert on the thing that they just screwed up on. Oh, let me explain to you why you're getting this error message. It's because in Daphne, you have to use this modify clause. Like, well, thank you. You're the one that made that mistake. Okay, so now it tells you to do this modifies clause. Now notice, this is actually not quite right, because modifies should just take the name of the entire array, not the arrays with their indices. So you get another array, but we just send this back to the LLM, apologizing for the confusion. Yes, apologies for the confusion. Yes, you should do it this way. So perfect on the third try. Okay. Now what's interesting here is we didn't actually do anything but just feed back the result of the Daphne compiler to the LLM, and it figured it out. Okay, so yeah. Okay, so I'm going to come to that. So this was our first experiment, which was just to sort of see, is it feasible that the LLM can generate some specifications? And it seems like yes. And in fact, do I have this? Yeah, okay. So yeah, I'm going to show you that in just a second. So we came up with this thing that we're calling Clover that's going to address some of these questions that have come up. So it's going to take 2 phases. So the first phase is just generating, right? And you can use, whatever you want. It could be written by humans. It could be written by AI, some combination, whatever. But we're going to take off phase 2 that's going to tell us how well we've actually done. And phase 2 is going to be more than just checking the spec, okay? What we're going to do actually is we're going to require that phase 1 generates a natural language documentation. It's going to generate the code, and it's going to generate the specification. And then we're going to check for consistency among all 3, okay? And only if all 3 of them are shown to be consistent in both directions, so that's 6 checks, will we give it a pass, all right? So true is not going to cut it, because true is not going to be consistent from annotation to code, even if it's consistent from code to annotation. All right, was there another question? Yeah. Yeah. No, I don't think that's true. Have to look at the code. But Daphne says it was correct. So, you know, there must be some, yeah, we'll have to look at it. But I trust, you know, Daphne runs an SMT solver. Unless there's a bug, you know, it should be right. Okay, yeah. Yeah, I'll come to that. I'll come to that. Mhm. No, handwritten. Yeah. So we hand wrote 50 examples that were not on the internet, right? So we didn't want it to be in its training set. But they are simple examples from textbooks. Yeah. All right. So let's look at this phase 2. This is where it gets quite interesting. So what we did is right. So we have this consistency checking that I'll go through in a minute. But we also we took those 50 examples, we added a few more, and then we wrote not just the code, we also wrote the specifications, and we wrote a natural language docstring for every one of these examples. Okay, so this is our data set, and we're going to do some things with it. What we would like is for our consistency algorithm to pass these 60 examples, because we hand wrote everything and it's correct. But if we change something in a bad way, we want it to reject it. Okay, so that's what we're going to test. All right, so here's the punchline. Of our 60 examples, the ones that are correct, we could accept 75% of them with our algorithm. And then just by doing repeated trials, we were able to accept up to 87%. All right, so it's pretty good. And actually, it's really good because we have a perfect record on rejecting anything that's wrong. And we biased our algorithm towards that. So if you do anything wrong, if there's any inconsistency in these 3 steps, we really want it to say no good. Now, we hope it most of the time also says that something that's correct is good. But just out of the box, I think this is pretty exciting. So we got 87% pass rate for good ones and a 100% reject rate for bad ones. All right, so how does this work? So here's an example. One of our little examples, it does integer square root. So you give it a natural number, and it should come up with the number that's closest to the square root of that number. Doing some while loop with an invariant in it, right? So this is the fully annotated example with the docstring, the annotations, the specification annotations, and the code. Right, so that's the docstring. This is the formal specification, and this is the code. Actually, interestingly enough, for the purposes of generation, the invariant is considered part of the spec, because we expect that the LLM generates both the preconditions and the invariant. But for the purposes of consistency checking, we actually consider the invariant to be part of the code, which is okay, because once you have everything, you can split it up however you want. That was a little bit of an interesting distinction we had to make. Let's see. Right, so for each benchmark, we had the correct version, and we had 3 wrong variants where we, either strengthened or weakened one of these ties between the 3 things we're checking. Okay, so let's go into a bit more detail on how this verification phase works. So we do 6 consistency checks. The obvious one is we check that the code actually adheres to its annotation, its specification. We just run Daphne, okay? And if Daphne says yes, then that means yes, the code satisfies its specification. Otherwise, this check fails. For these simple examples, I think, well, yeah, I think there's a little bit of selection bias. I think we selected problems that we knew Daphne would work on because we weren't trying to test Daphne, right? But yeah, for more difficult problems, that would be an issue. And one of the outcomes, I think, of this research is we need, even more better tools for deductive verification if we want to scale this up. Okay. The annotation complete check, this is kind of interesting. So what we do is we actually give ChatGPT just the annotation, just the pre and post conditions, and we say, generate some code that meets these pre and post conditions. All right, so it gives us back some Daphne code, and then we actually do some unit testing to see if the generated code has the same behavior as the original code. That's what it has to do to pass that test, okay? All right. Now, the ones with the doc strings are maybe the most sketchy, because basically what we do is we say, here's the annotation, now write a natural language description of it. And now we're going to ask another LLM whether those two natural language descriptions say the same thing. Okay, so this one is actually kind of one of the weaker ones. But this is actually kind of cool. Going the other direction, you say, here's the natural language description, and you ask the LLM to generate the spec from that. Then you actually call Daphne to prove that the generated spec is equivalent to the original spec. So that we get a pretty strong guarantee there as well. All right, and then you do similar things here with the code. All right, so we're going to check all of these things, and only if it passes all 6 tests do we give it the thumbs up. Right, so like I said, how do you check equivalence? Right, basically what we're doing is we take something, generate another thing, and then try to see if it's equivalent to the original thing. So that equivalence check is just for doc strings, we ask ChatGPT. For code equivalence, we use unit tests, but you could use something stronger, some kind of formal equivalence checking. And then for annotation equivalence, you can use the formal tool. Right, so here's an example of docstring equivalence, right? The original thing says find the square root of a natural number. The generated thing, of course, is very verbose. But ChatGPT says, yes, both docstrings describe the same functional behavior. All right, so good. For code equivalence, this just shows we have like 5 tests, and we're just going to check that they do the same thing on all 5 tests. For annotation equivalence, we use this little template to prove that that the pre and post conditions are equivalent in both cases. Right, okay, so then yeah, go ahead. Yeah. Well, you're right. It's not that particular part is a weak link, but it also, is opens the door for more research, right? So somebody needs to go work on semantic matching in doc strings. So let's make that better. Somebody needs to work on better verification tools. Somebody needs to work on better generation of specifications with LLMs, right? So there's like multiple PhDs worth of research to do to improve this. Yeah, so we just sort of have given the first steps. What's good is that some of these checks are already very, very strong. And probably if we didn't even do the docstring check, we would still get our good results. So that's why we're getting good results. All right, so let's look at some experiments. So for the generation, yeah. Why not just 4? Redundancy. Yeah. I mean, we haven't really done a careful study to see if you need those things because, again, we don't have enough data. This is really all just kind of a first step into the unknown, right? But yeah, you should, there are many more things to consider. Maybe you should also have unit tests, right? Maybe it should be a 4-leaf clover. Maybe you should, maybe some of those arrows don't really help at all. Yeah. Okay. So for phase one, we asked the question, so phase one is generation, right? And you might imagine lots of things that could happen. Maybe you have a legacy code base and you just want the LLM to generate the spec. Or maybe you have a natural language spec, you want to generate both. Or maybe you actually wrote down your formal spec and you just say generate the code. I think there are lots of possibilities. So we looked at two. So one was given the formal spec, generate the code. And the other one was given the code, generate the spec. And we had a few tricks we could use to improve things. But for code generation, it actually 53 was able to generate 53 out of 60 of our programs correctly. So it's pretty good. For annotation generation, after some improvements, it was able to generate 41 out of 60 correctly. So not great, but still, you know, the majority of the time it's actually generating correct specifications, which I probably wouldn't have predicted. Especially since, you know, the LLMs haven't really been trained on Daphne code. And in fact, the Daphne code they have seen is an older version of Daphne, because we know this because it was often making syntactic errors that were in favor of the old syntax. So I think this could be improved quite a bit with some specialized training. Right, and then these are the results. Let's see, we already saw. So drilling down a little bit, which of the tests succeed or fail? For the ground truth ones, this shows you where they succeed and fail. So the Daphne checks succeed all the time, so that's great. Let's see, anything that's generating doc strings succeeds most of the time, because the docstring equivalence check is pretty weak. And then some of these other ones do fail occasionally, and often it's because it's generating, you know, Daphne code with bad syntax or something. So this could be improved, we think. For the incorrect variants, yeah, we just tweak one of the three parts, and this is, you know, you can dig into this. One thing that's kind of interesting is that just the documentation to annotation arrow actually rejected everything. So this thing where you say, here's the spec, generate the formal specification for it, and then check formally if it's equivalent to the real specification, that somehow managed to just rule out all the bad examples. So that seems like a very powerful check. Some of the other checks, not quite as powerful, but everything together, you know, tells a consistent story. Okay, so what are some limitations? There are a lot. Certainly the LLMs, you know, they're quite powerful today, but they haven't really been designed to do this task. And there are a lot of limitations showed up in the experiments. Either they didn't understand Daphne well enough, or, you know, they gave some redundancy or some, you know, poorly worded specifications or things. All of these things I think can be improved a lot. The other thing we didn't really try is all of these, you know, chain of thought, tree of thought, all of this stuff where you can get, where the LLM actually knows a lot more than it's telling you on the first try. I think this could all be done. You know, you could ask it, for example, if it gives you a bad spec, you could say, you know, I don't think that's a good spec. Why don't you simulate the code and tell me each step? You know, have it do that once or twice. Now tell me the specification, right? I bet it would get it right more often. Okay. Right now, we're focusing on purely functional capabilities, right? So if I have a bubble sort and a quick sort, then we'd consider those equivalent as long as they have the same functional behavior. I think that's already, you know, a pretty big challenge, but, you know, maybe you'd like to have the ability to talk about performance and other kinds of specifications. Okay, and then there is some small chance that it could pass the whole Clover check and still be wrong because somehow it managed to you know, the thing you originally wanted is not the artifact that you got. I would argue that as long as the human generated one of those three pieces and Clover says they're consistent, then probably it's consistent, unless the human didn't really know what they wanted, which is also, of course, a big possibility. Okay, so basically, early results are quite promising, I think. And maybe we have a roadmap to heading off this dystopian future where all of our code is written by AI and none of it is verified. All right, so just to summarize, I think AI and AR are powerful complementary technologies, and together they can help improve both the trustworthiness and scalability of applications. All right, so that's it.
Questions?
So as a result of these experiments, did you find as you were querying the LLM, presumably the same LLM, over these experiments, did you find the quality of the code that it generates improving? Was it seeing that?
No. So we always started a new session with every experiment. So we weren't doing everything in the same context window.
Oh, I see.
Yeah, and as far as I know, you know, ChatGPT-4 is not being retrained on anything we're doing, you know, on the fly. So
I see.
What is interesting is that it doesn't always give you the same result, right? And of course, LLMs are designed to do that. So that's why one of the graphs, it had this K parameter. And what we would do is if the task failed, we would just try to do the same task like 10 times. And often if you do that, you know, one or two of them succeed and you just need one. That's what's one of the really sort of fun things about this approach is the LLMs can be wild, right? They can do whatever they want. And then, you know, they get shunted into this room where they get very carefully worked over and make sure that everything's correct. So I kind of like this division of labor. Yeah.
So the doc string that you hand wrote was probably smaller, but the doc string that the LLM generates is actually more verbose.
Yes.
So I think you had to do some NLP like to match the equivalence of the
That's right.
text.
In fact, all we did was ask another LLM. Yeah, we just said, hey, do these two doc strings say the same thing? And that is one of the weaker parts. I think semantic matching of NLP strings is a totally separate and interesting research direction. And as that improves, that will help our tool. Yeah. Yeah. I think it's just a yes or no at this point. It's just say, are these two doc strings giving you, describing the same functional behavior? Yeah. Right. I think there's a lot of room for sort of drilling down into all the building blocks of what we're presenting and improving each of those building blocks.
Saying like the only thing it was doing is experiment with it, it was rejecting the good things.
Doc to code. Let's see. Yeah, so it rejected 4 out of 60 of the good things. And what did it do? Yeah, that's right. Yeah, but this is a small sample, right? So I don't know. I'm a cautious guy, right? So I want 6 checks. Maybe someone out there will say, all I need is 1 check and I'm happy. But I want to at least start off being very conservative.
Yeah, my point is that you ask it to do a big task. I do really like it. I often find it that it is always going to make some errors. So if you start to text to code, so asking it to the two code that are going to match, so we have to too much.
Right, right. Yeah, I mean, one of the things we didn't explore in this work, which is another whole thing, is how can you use some synergy to improve the generation, right? So maybe you say, all right, generate me the spec and the code. You run the Clover test, it says no. Now, how do you use that information to go back and generate again? And I bet, you can do a feedback loop that gets a lot more done. Yeah. Yeah.
What was it better at generating specs or code?
It was better at generating code. Yeah. Yeah. So it's maybe not too surprising. There's a lot more code out there than specs.
I think there is division, right? So there is spec, and okay, so so one is the spec, which is the precondition, post-condition, but then there are also these invariants. And I would suppose that it might get the pre-post correct, but the invariance is something it might struggle out. So did you notice that?
So for these simple programs, it seemed to be pretty good with the invariants. Yeah, but I think you're right. Obviously, coming up with invariants is a hard problem in general. There's some other work though so other people have been looking just specifically at generating invariants with LLMs, and there's also some promising work in that direction. Actually, my student, the one that's on every paper, Hausa, he also wrote a paper about using LLMs to generate invariants, which is pretty cool. Like basically he could take a software model checker, augment it with an LLM, and like boost its performance significantly. Yeah. So this is also on arXiv. You can check it out.
Could you use the LLM to generate any test cases?
Yeah, I think you could. So in fact, as we were preparing this work, one of my students wanted to do this, right? That's why I talked about the 4-leaf clover. And I said, no, that's future work. Let's stick with a 3-leaf clover for now. But yeah, that would be an interesting thing to try. There is some work on using LLMs to generate test cases, and I think it's a bit tricky. I think it has not been as successful as you might like. To be honest, I think it's easier to generate a spec than it is to generate a good test case. Because you actually kind of have to know the spec to generate a good test case. Anyway, that's all sort of stuff to be explored.
Okay, one more question. Could you think of, or could you try using the LLM to reason correctness of the code instead of using a model checker or a Daphne-like tool?
You could, but I feel like that would be asking the wrong tool to do the wrong job, right? Because you have no guarantee that it's going to get it right. Whereas if I use a formal tool, I do have that guarantee. So I would like the LLM to do everything all the way up until it comes time to check, but I'd like the check to be done by a formal tool. But I think there is the opportunity for the two to work more collaboratively. I think that would be really interesting because I think you could get the LLM to give you a better spec if you asked it to do that reasoning, right? So maybe that would be a valuable thing to try. But for my money, please run the formal tool at the end, right? Make sure it's correct.
So was the prompt size a limitation?
No, because we were doing little small functions. I guess if you wanted to do some really big, system, it could be. Although, so one of the next things we want to try is, just like any good PL researcher, we go from single procedure to interprocedural reasoning. And what's nice is deductive verification has already solved this problem, right? So what you can do is you have a function, it calls some other function, you just replace the function calls with the pre and post conditions, and then you can reason about everything modularly. And Daphne supports this. So you shouldn't have to feed it the entire code base, it should be enough to just feed it a function at a time. Now, if you want to get those interfaces between the functions right in generation time, you might need to feed it more than that, and that's something we're exploring. But yeah, the prompt size hasn't been an issue so far.
Also, I guess related to the question that was just asked, there is this recent results that show chain of thought reasoning is more powerful than one shot.
Yes.
So have you tried that?
So we tried it a little bit by feeding, like if the Daphne verification fails, then we feed it back and say, hey, it failed, can you give me a better spec? So that we did it just in that limited way, but I think there's a lot of opportunity to do more, right? And in particular, if it gives you a bad specification or a specification that you know is wrong, you could ask it to, use chain of thought to reason about this program, like step through it, and maybe then it could figure out what the right spec is. Yeah.
So would you use LLM to generate an automated reasoning tool?
I think you can. Yeah, I mean, certainly it can write SAT solvers, right? But yeah, that would be interesting. So I think there's a whole interesting question of, how far can you push this? Could you actually ask an LLM to write a complex system and prove it's correct using this kind of technique? And I don't know. I hope that eventually, yes, we could do that.
Here the automated reasoning tool is something on which you have confidence because it is not generated by an LLM.
Right,
And
right.
so you can
Well, you have
repair
to bootstrap, right? So you would start with some handwritten, trusted code, but you could ask the LLM to generate and to write a verified automated reasoning tool, right? That's verified by that code. Then you could use the verified automated reasoning tool to go forward. Yeah. Someday, I think this would be really cool.
Yeah, I just quickly wanted to ask, you're mentioning ChatGPT. So what version, or have you tried other LLMs?
Yeah,
between
we
versions
used ChatGPT 4, just using the API online, and basically everything else we tried is terrible. So the problem, even if you like fine tune a 9 billion parameter model on Daphne, it's like nowhere near as good as GPT-4. So we have this big problem in research right now, which is GPT-4 is way up here, and anything we can like mess with is way down here, which makes it hard to, really do good science. So I hope somebody solves that problem.
Okay. Are there other questions? All right. So if not, let's thank Clark for a very interesting talk. And yeah, thanks, Clark. So with that, we come to the end of the Sat+Smt Winter School 2023. So this is just a sneak peek of the next SAT conference is going to be held in India, in Pune, from August 21st to 24. And the next Sat+Smt school will be just before the SAT conference from 18th to 20th August. So please attend that, submit your papers, and hopefully we'd have more advances in this area by then. So to conclude, I would like to thank various people and various organizations that were instrumental in making this event possible. So thanks to IIIT Hyderabad and particularly Registrar Professor Rajan for allowing us to use all of these facilities and for all the arrangements. The local organizing committee, particularly Suryajit and Girish, and Mr. Srinivasulu for the local transportation arrangements, the registration desk, which was handled by Soumya, Vidya, Nitish, Keval, Atul, Farkhan, Aryaman, and Prerna. Thanks to all of them. The lunch, tea, coffee, which was all the coordination was done by Professor Gautam. financial things were managed by ACM India, and of course the sponsors, which were TCS Research, CISPA, Qualcomm, and IARCS. Thanks to all of them for making this happen. And thanks to all of you for coming. And of course, our invited speakers. I mean, they all made this program worth it. So Clark, Kiran, Shubhajit, Mate, Kuldeep, Arijit, everybody. You know, I don't have all the names off the top of my head. So thanks everybody for coming, and we'll see you in the next edition, which will be just before the SAT conference. And till then, have a good time. So there are some flyers for the SAT conference. If you want to take it back to your organization, put it up on the notice board.